For decades, the idea of humanity becoming a multi-planetary species has been treated as an eventual certainty. From Mars colonization plans to visions of orbital cities and self-sustaining off-world settlements, the narrative has been consistent. Earth is just the beginning. Governments, private space companies, and popular science media often frame space expansion not as a question of if, but when. The assumption is that technological progress will naturally carry us beyond our home planet, just as it carried us across oceans and into the sky. But beneath the optimism lies a deeper, less discussed reality. When examined through physics, biology, economics, engineering, and long-term systems stability, the idea of permanent, independent human civilizations beyond Earth begins to break down. This documentary examines the single underlying reason that connects every failed model, collapsed simulation, and unresolved constraint, and why, despite our ambitions, humanity may never truly become multi-planetary. The core assumption behind multi-planetary dreams. The belief that humanity will become a multi-planetary species rests on one central assumption, that space colonization is primarily a technological problem. In this view, once rockets become powerful enough, life support systems efficient enough, and habitats advanced enough, permanent settlement beyond Earth becomes inevitable. This assumption shapes policy decisions, private investment, and long-term planning across the space industry. However, history shows that treating colonization as a purely technical challenge ignores deeper constraints that technology alone cannot solve. This assumption persists largely because technology has solved many past limitations. Aviation overcame distance. Telecommunications overcame isolation. Medical advances extended lifespan. These successes encourage the belief that space represents a similar barrier waiting to be engineered away. Yet space is not an extension of Earth's environment. It is a fundamentally different domain governed by constraints that do not scale down with innovation. The laws of physics, biology, and systems reliability impose limits that improvement does not erase, only delays. Every proposal for off-world settlement begins with transport. Rockets must move people, equipment, food, and infrastructure out of Earth's gravity well. While launch costs have decreased significantly over the past 2 decades, they remain enormous when measured against the scale required for true colonization. A single human requires thousands of kilograms of life support mass per year when accounting for air recycling systems, water processing, radiation shielding, spare parts, and redundancy. Transporting this mass repeatedly, safely, and indefinitely introduces compounding costs that no launch system has yet overcome. Transport is not a one-time hurdle. It must be sustained across generations. Every failure, delay, or accident imposes cascading consequences. Unlike terrestrial logistics, there are no alternative routes, no rapid resupply options, and no local industrial base capable of replacing lost capacity. Even with reusable launch systems, the energy cost of lifting mass from Earth remains fixed by gravity, not innovation. Once humans arrive at another world, the problem shifts from transport to survival. Earth is not simply a place humans evolved on, it is an active life support system. Its atmosphere regulates temperature, blocks radiation, recycles carbon, and maintains pressure within a narrow biological tolerance. Its magnetic field deflects solar and cosmic radiation. Its geology recycles nutrients over millions of years. Its biosphere absorbs waste and stabilizes chemical imbalances. No other known location in the solar system provides even a fraction of these protections. Replacing them artificially requires continuous energy input, constant maintenance, and perfect system reliability. Mars, often presented as the most viable alternative, illustrates this clearly. Its atmosphere is less than 1% the density of Earth's, offering virtually no radiation protection. Its lack of a global magnetic field exposes the surface to solar particle events that would be lethal over long periods. Average surface temperatures are far below freezing, and dust storms can last for months, reducing solar power generation precisely when energy is most needed. Any human presence on Mars would exist entirely inside sealed environments, dependent on machines that must never fail. Closed-loop life support systems are frequently cited as the solution. In theory, air, water, and waste can be endlessly recycled. In practice, no closed ecological system has ever operated indefinitely without external intervention. Experiments such as Biosphere 2 demonstrated how small imbalances in oxygen, microbial activity, or material degradation can cascade into systemic failure. These failures occurred under controlled conditions on Earth, with immediate access to repair resources and human intervention. Replicating stability millions of kilometers away introduces risks that compound over time rather than diminish. Radiation exposure presents another constraint that technology has not solved. Outside Earth's protective magnetic field, astronauts are exposed to cosmic rays capable of damaging DNA, increasing cancer risk, and degrading neurological function. Shielding against this radiation requires thick layers of mass, often measured in meters of water, soil, or metal. Transporting such shielding from Earth is impractical, while sourcing it locally assumes mining, processing, and construction capabilities that do not yet exist and may never be economically viable at the required scale. Even if physical survival could be maintained, long-term human health remains unresolved. Microgravity environments cause bone density loss, muscle atrophy, cardiovascular deconditioning, and changes to vision and brain structure. Artificial gravity through rotation has been proposed, but building and maintaining large rotating habitats introduces engineering challenges far beyond current capabilities. Partial gravity environments, such as Mars gravity, have never been tested over a human lifetime, and their biological effects remain unknown. Economics further undermines the assumption of inevitability. Earth supports space activity because it provides resources, labor, infrastructure, and markets. Off-world settlements would initially produce nothing of economic value that could justify their cost. Mining asteroids or other planets is often suggested, but raw materials in space must still compete with Earth-based resources that are cheaper to extract, process, and transport. Without a self-sustaining economic loop, off-world settlements remain permanently dependent on Earth. Dependency is the key issue that challenges the multi-planetary narrative. True multi-planetary status requires independent civilizations capable of surviving without Earth's support. Every current proposal, including Mars bases and lunar habitats, depends on continuous resupply, technical expertise, and industrial production originating from Earth. Any disruption, political, economic, or environmental, would immediately threaten off-world populations. Finally, time itself works against colonization. Machines degrade, materials fatigue, human systems accumulate entropy. A settlement that survives for 5 years, 10 years, or even 50 years is not a new civilization. It is an outpost. The longer a system operates in isolation, the more failure modes emerge. Maintenance requirements grow rather than shrink. Complexity becomes a liability rather than an asset. The assumption that technology alone can overcome these realities is the foundation upon which multiplanetary optimism is built. But when examined across physics, biology, and systems engineering, this assumption begins to fail. The challenge is not reaching another planet. It is sustaining human life there indefinitely, without Earth, in an environment fundamentally hostile to biology. This is where the core limitation begins to reveal itself, and where the idea of becoming truly multiplanetary starts to break down. Earth is not a location, it is a system. One of the most persistent misunderstandings behind the idea of becoming multiplanetary is the way Earth itself is conceptualized. Earth is often treated as a place, a physical location that humanity happens to occupy. In reality, Earth is a tightly coupled, self-regulating system that supports life through countless interacting processes operating across scales of time and space. This distinction matters because leaving Earth does not mean leaving a location. It means leaving a system that cannot be meaningfully replicated elsewhere. Life on Earth is sustained by an intricate balance between atmosphere, oceans, geology, and biology. Oxygen levels are maintained through photosynthesis and carbon cycling. Temperature is regulated through atmospheric composition, ocean currents, and cloud formation. Water is continuously purified, redistributed, and recycled through evaporation, precipitation, and biological activity. None of these systems operate independently. They are interlocked feedback loops that evolved together over billions of years. Removing humans from this system removes them from the very processes that keep them alive. When space colonization is discussed, these processes are often reduced to simplified substitutes. Oxygen becomes a chemical reaction. Water becomes a filtration problem. Food becomes a controlled agricultural system. While these replacements can function temporarily, they lack the redundancy, adaptability, and resilience of Earth's natural systems. On Earth, failure in one subsystem is often compensated by others. In artificial environments, failure propagates rather than dissipates. Consider atmospheric stability. Earth's atmosphere maintains pressure, temperature, and composition within narrow ranges compatible with human life. It does so through mechanisms such as carbon sequestration in oceans, weathering of rocks, and biological respiration. Artificial habitats must maintain these same conditions through sensors, mechanical systems, and human oversight. A minor sensor failure, software error, or material leak can destabilize the entire environment. Unlike Earth's atmosphere, there is no margin for error and no natural recovery pathway. Food production illustrates the same problem. Terrestrial agriculture relies on complex soil ecosystems composed of microbes, fungi, insects, and chemical gradients that regulate nutrient availability. Attempts to recreate food systems in space typically rely on hydroponics or controlled soil substitutes. These systems are efficient in the short term, but fragile over time. Pathogens can spread rapidly, nutrient imbalances accumulate, genetic diversity declines. On Earth, agricultural failures can be offset by imports, climate variation, and ecological diversity. In isolation, failure is absolute. Water cycling presents another constraint. Earth's hydrological cycle purifies water naturally through evaporation, condensation, and filtration through geological layers. Space habitats must recycle water mechanically, achieving near-perfect efficiency to survive. Even a 99% recovery rate becomes catastrophic over long periods as losses compound. Replacement water must then be imported or extracted locally, assuming accessible sources exist and can be processed reliably. Energy production further exposes the system problem. Earth receives a constant, stable energy input from the Sun, moderated by atmosphere and magnetic shielding. Solar energy on Mars or the Moon is intermittent and vulnerable to environmental disruptions such as dust accumulation and eclipses. Nuclear power offers stability but introduces long-term risks related to maintenance, fuel supply, and waste management. Energy failures in closed systems are not inconveniences, they are existential threats. Perhaps the most underestimated component of Earth's system is its magnetic field. This invisible shield deflects charged particles from the Sun and cosmic radiation from deep space. Without it, Earth would slowly lose its atmosphere, as Mars did. Artificial habitats cannot replicate a planetary-scale magnetic field. Shielding can reduce exposure, but cannot eliminate it. Over decades, accumulated radiation damage affects both human biology and electronic systems, increasing failure rates in ways that are difficult to predict or mitigate. Psychological and social systems are also part of Earth's life support network, though they are rarely acknowledged as such. Humans evolved in open environments with natural cycles, social diversity, and sensory variation. Long-term confinement in artificial habitats introduces stresses that degrade mental health, social cohesion, and decision-making. Studies of isolated environments on Earth, such as polar stations and submarines, consistently show rising conflict, depression, and cognitive decline over time. These effects worsen as isolation lengthens and options for exit disappear. The concept of independence is where the system reality becomes unavoidable. A truly multi-planetary species would require off-world populations capable of surviving without Earth's intervention. This means producing spare parts, advanced electronics, medical equipment, and industrial tools locally. It means educating specialists, maintaining scientific knowledge, and adapting to unforeseen crises without external support. Every one of these requirements assumes an industrial ecosystem comparable to Earth's, something that took thousands of years and billions of people to build. Attempts to bootstrap such complexity from small initial populations face a fundamental scaling problem. Industrial systems rely on specialization, supply chains, and economies of scale. A settlement of a few hundred or even a few thousand people cannot sustain the diversity of skills and production needed to replace Earth's industrial base. As population increases, resource demands grow faster than local production capacity, reinforcing dependency rather than reducing it. This dependency creates a fragile equilibrium. As long as Earth remains stable and capable of providing support, off-world habitats may persist, but this does not represent a new planetary civilization. It represents an extension of Earth's system into hostile environments, connected by supply lines that must function perfectly across vast distances. Any disruption to those supply lines, whether due to political conflict, economic collapse, or planetary crisis, would rapidly cascade into failure. The key insight is that Earth is not simply where humanity lives. It is what enables humanity to live. The planet's systems perform functions that no technology has replicated at scale or over long durations. Leaving Earth means abandoning these systems and replacing them with artificial approximations that degrade over time rather than strengthen. This is not a temporary limitation that disappears with better engineering. It is a structural constraint rooted in how complex systems function. Understanding Earth as a system rather than a location reframes the entire multiplanetary debate. The question is no longer how to move humans elsewhere, but whether any environment without Earth's integrated systems can sustain human civilization indefinitely. As the evidence accumulates, the answer becomes increasingly uncertain, and it leads directly to the deeper limitation that ultimately defines why becoming truly multiplanetary may never be achievable. Another way to understand Earth as a system is to recognize how deeply time is embedded into its operation. Earth's stability is not the result of static conditions, but of continuous adjustment across geological, biological, and atmospheric timescales. Volcanic activity replenishes atmospheric gases. Plate tectonics regulates carbon through rock weathering. Evolution adapts organisms to shifting environments. These processes operate slowly, but their cumulative effect is resilience. Artificial habitats operate on mechanical timescales measured in hours, days, and maintenance cycles. When systems drift, they do not self-correct. They require intervention. Over long durations, this difference becomes decisive. Earth's oceans illustrate this temporal buffering. They absorb heat, redistribute energy, and stabilize climate across centuries. No artificial reservoir can replicate this capacity. Temperature control systems respond only after deviation occurs, consuming energy and stressing infrastructure. As habitats grow larger, this lag becomes more dangerous. Small fluctuations that Earth absorbs silently become emergencies in engineered environments. Earth also externalizes waste naturally. Excess heat radiates into space through planetary-scale processes. Chemical byproducts are diluted, buried, or transformed biologically. Artificial systems must internalize waste handling entirely. Nothing leaves the system unless deliberately expelled, and expulsion itself requires energy and mass loss. Over time, inefficiencies accumulate. Filters clog. Byproducts concentrate. Maintenance loads increase. The system perspective also reveals why redundancy on Earth works differently. Redundancy in nature is distributed and decentralized. Multiple species perform similar roles without coordination. Failure does not propagate uniformly. In engineered systems, redundancy is centralized and planned. Components share dependencies. When a common input fails, backups fail with it. This is why Earth recovers from disasters while artificial systems do not. Wildfires, storms, and extinctions reset local regions, but leave global function intact. A comparable failure in a closed habitat threatens total loss. There is no outside context to absorb shock. Seen this way, leaving Earth is not analogous to settling a new continent. It is closer to attempting to recreate an entire planet inside a machine. The challenge is not insufficient technology, but insufficient system depth. Until an off-world environment can replicate Earth's layered, time-integrated resilience, it remains dependent by definition. This distinction explains why optimism often outpaces feasibility. Human planning favors linear problems with clear endpoints, while Earth's system operates through nonlinear interactions without a finish line. As complexity increases, predictability decreases. Off-world environments demand perfect foresight, yet perfect foresight is impossible. Each additional subsystem multiplies unknowns rather than resolving them. Over time, this accumulation transforms risk into certainty. A system that must work forever will eventually fail. Earth endures because it does not require perfection. Artificial worlds do. They persist only through constant correction, consumption, and oversight. Conditions incompatible with permanence, autonomy, and long-term civilizational stability beyond Earth's system itself. The scale is the barrier. A second, deeper obstacle to becoming multiplanetary emerges once Earth is understood as a system rather than a location. Even if humanity could partially replicate Earth's life support processes, there remains the issue of scale. Civilization functions at a scale that far exceeds what off-world environments can realistically support, and this mismatch is not a temporary engineering problem, but a structural limitation. Modern civilization depends on massive populations concentrated within interconnected networks. These populations support specialization across thousands of fields, from advanced materials science to semiconductor fabrication, from medical research to industrial agriculture. Each field depends on countless others. The production of a single microchip, for example, requires global mining operations, chemical processing facilities, precision manufacturing plants, logistics networks, and a trained workforce distributed across continents. This complexity does not shrink easily. Off-world settlements are often imagined as small, self-sufficient communities that gradually expand. In practice, scaling such communities introduces compounding constraints. Every increase in population multiplies demand for energy, food, water, housing, medical care, education, and governance. On Earth, these demands are distributed across vast territories and buffered by trade. On another planet or in space, they must be met locally, under harsher conditions, with fewer resources and far less redundancy. Population size is not simply a matter of numbers. It determines whether a society can sustain knowledge. Specialized expertise requires training pipelines, mentorship, institutional memory, and ongoing practice. A settlement with a few thousand residents cannot support the breadth of expertise required to maintain advanced technology indefinitely. Skills decay. Equipment fails. Without constant replacement and retraining, technological regression becomes inevitable. Industrial production highlights the same issue. Earth's industries rely on massive extraction operations that process millions of tons of material annually. These operations depend on gravity, atmospheric pressure, and ecosystems that absorb waste. Replicating heavy industry off-world would require enormous infrastructure investments before producing even minimal output. Transporting raw materials within low-gravity environments introduces inefficiencies that increase wear, energy consumption, and failure rates. Energy scaling presents a particularly severe constraint. Industrial civilization consumes energy at levels that dwarf the output of localized systems. Solar energy on Earth benefits from atmospheric diffusion and planetary scale collection. On Mars or the Moon, solar collection is intermittent and surface limited. Nuclear energy can provide higher output but requires complex fuel cycles, safety systems, and long-term waste management. Scaling nuclear infrastructure safely in isolated environments introduces risks that compound with population growth. The issue of waste is often overlooked but critical. Earth's biosphere absorbs waste through biological and geological processes. Carbon is cycled, toxins are diluted, and heat is dispersed. In closed or semi-closed systems, waste accumulates. Heat rejection becomes increasingly difficult. Chemical byproducts concentrate. Managing waste at small scales is challenging, but possible. Managing it at industrial scales without Earth's buffers becomes a dominant limiting factor. Economic scaling adds another layer of difficulty. Earth's economy functions through specialization and trade. No region produces everything it needs. Off-world settlements would need to either replicate this economic complexity internally or remain dependent on Earth. Replication requires population growth beyond sustainable limits. Dependence undermines the premise of multi-planetary independence. Transportation costs amplify these constraints. Moving people and materials between planets requires energy expenditures, orders of magnitude higher than terrestrial transport. Even with optimistic advances in propulsion, launch windows, orbital mechanics, and fuel requirements impose rigid limits. Supply disruptions that would be inconvenient on Earth become fatal in isolated environments. Social systems also scale poorly in constrained habitats. Governance becomes more difficult as populations grow under confinement. Conflict resolution, law enforcement, and political legitimacy face pressures intensified by limited resources and the impossibility of relocation. Historical examples of isolated societies show increased volatility, not stability, as scale increases without corresponding environmental capacity. Biological scaling imposes limits that technology cannot bypass. Human reproduction introduces genetic constraints in small populations. Avoiding inbreeding requires larger populations than early settlements can sustain. Medical emergencies become statistically inevitable as numbers grow, yet advanced care depends on specialized equipment and personnel. Each solution increases system complexity and vulnerability. The idea that expansion solves these problems misunderstands the nature of scaling. Growth does not linearly increase capacity, it increases strain. Earth can absorb that strain because its systems operate at planetary scale. Off-world environments cannot. Every added person tightens constraints rather than relieving them. This leads to an uncomfortable conclusion. Humanity does not fail to become multi-planetary because of insufficient ambition or technology. It fails because civilization itself only functions at scales that hostile environments cannot support. Earth provides a unique combination of size, stability, and systemic integration that allows complexity to flourish. Remove that foundation and scaling becomes self-defeating. As plans for off-world expansion grow more detailed, this scaling barrier becomes harder to ignore. It forces a reassessment of what multiplanetary actually means, and whether sustaining civilization beyond Earth is even compatible with the way civilization operates. Scale also determines resilience in the face of unexpected shocks. On Earth, when supply chains break, alternatives often exist. A factory failure in one region can be offset by production elsewhere. Crop losses in one climate zone can be compensated by harvests in another. These substitutions rely on geographic diversity and surplus capacity distributed across the planet. Off-world settlements lack this buffer entirely. A single point of failure remains a single point of failure no matter how advanced the technology surrounding it. Maintenance burden grows non-linearly with scale. As systems multiply, so do interfaces, dependencies, and inspection requirements. Each airlock, habitat module, power conduit, and processing unit introduces additional failure modes. On Earth, maintenance labor is drawn from a vast population trained across generations. In isolated settlements, maintenance competes with every other survival task. Deferred repairs accumulate silently until cascading failures emerge, often without warning. Communication delay further complicates scaling. Earth-based civilization relies on near-instant coordination. Financial markets, emergency response, and industrial logistics assume real-time information exchange. Interplanetary distances impose delays measured in minutes or hours. Decision-making becomes slower and less precise, just as systems become more complex. Errors propagate before corrections arrive, amplifying instability rather than containing it. Scaling also interacts with human behavior in ways rarely modeled. Larger populations require formal institutions, enforcement mechanisms, and conflict mediation structures. These systems consume resources and attention. In constrained habitats, institutional overhead competes directly with life support needs. Political disputes that would be manageable on Earth become existential threats when access to air, water, or energy can be restricted by small groups. Attempts to automate away these issues encounter their own limits. Automation reduces labor but increases system opacity. Highly automated environments depend on software, sensors, and control algorithms that few individuals fully understand. When automation fails, recovery requires expertise that may not be present locally. Earth tolerates such fragility because external support exists. Off-world settlements do not. The cumulative effect of these factors is that scale does not unlock sustainability, it undermines it. Small systems are fragile because they lack redundancy. Large systems are fragile because they exceed environmental capacity. Earth alone occupies the narrow window where scale and stability align. Everywhere else, scale pushes systems toward brittleness. This reality reframes proposals for gradual expansion. Growth does not lead toward independence, but toward deeper entanglement with Earth-based support. Each added layer of complexity increases the number of assumptions that must hold indefinitely. Over time, the probability that all assumptions remain valid approaches zero. Understanding scale as a barrier does not diminish human ingenuity. It clarifies its boundaries. Civilization is not a portable object that can be resized and relocated at will. Persist without Earth, expansion becomes unsustainable rather than permanent civilization. Closed systems always drift toward failure. Once scale is recognized as a limiting factor, the next barrier becomes unavoidable. Any attempt to sustain human life beyond Earth depends on closed or nearly closed systems. These systems must manage air, water, food, energy, waste, and human health continuously, without interruption, for decades or centuries. The problem is not that closed systems cannot function at all. The problem is that they cannot remain stable indefinitely. In engineering, closed systems are known to drift. Even when designed with extreme precision, small inefficiencies accumulate over time. Filters lose effectiveness. Chemical balances shift. Mechanical components wear down. Sensors slowly lose calibration. On Earth, these deviations are often absorbed or corrected by external inputs and natural buffers. In space or on another planet, there is no external environment capable of stabilizing the system when drift occurs. Life support experiments have demonstrated this repeatedly. Even carefully designed habitats struggle to maintain long-term equilibrium. Oxygen levels fluctuate as biological processes change. Carbon dioxide accumulates unevenly. Trace gases build up in unexpected ways. Microbial populations shift, sometimes becoming pathogenic. Each correction introduces new variables, which themselves require further correction. Over time, complexity increases, while reliability decreases. One of the most well-known demonstrations of this problem occurred during large-scale closed ecosystem experiments on Earth. These projects attempted to simulate self-sustaining habitats by sealing participants inside controlled environments with plants, soil, and recycled air and water. Despite access to Earth-based support teams and emergency intervention, systems destabilized within months. Oxygen levels dropped. Food production fell short of projections. Unanticipated chemical reactions altered atmospheric composition. Human health declined. These failures were not due to poor engineering or lack of funding. They occurred because biological systems are inherently dynamic. Living organisms adapt, mutate, and interact in ways that resist long-term predictability. On Earth, this dynamism is an asset because it allows ecosystems to recover from shocks. In closed environments, it becomes a liability. Adaptation does not necessarily align with system stability. Mechanical systems suffer similar problems. Machines operating continuously in isolated environments experience higher failure rates than those on Earth. Dust accumulation, radiation exposure, and thermal cycling degrade materials. Lubricants break down. Electronics suffer from cumulative radiation damage. Redundancy can delay failure, but redundancy itself adds mass, complexity, and additional failure points. Maintenance becomes a dominant challenge. On Earth, industrial maintenance relies on global supply chains, specialized repair facilities, and rapid replacement of failed components. In off-world habitats, every replacement part must either be manufactured locally or transported across vast distances. Local manufacturing requires raw materials, precision tools, and skilled labor. Transport requires energy, time, and alignment of orbital mechanics. Delays are inevitable. Human error compounds these risks. No system is immune to mistakes, especially under stress. Fatigue, psychological strain, and interpersonal conflict increase error rates. In closed systems, even small mistakes can propagate rapidly. A misconfigured valve, a delayed repair, or an incorrect software update can destabilize multiple subsystems simultaneously. Time magnifies every weakness. Systems designed to function for months may not function for decades. Systems designed for decades may not function for centuries. Every long-term projection assumes consistent performance from components that degrade and environments that change. The longer the system operates, the more it diverges from its original design assumptions. Biological recycling introduces additional uncertainty. Waste processing depends on microbial communities that can shift unpredictably. Nutrient recycling relies on chemical pathways sensitive to temperature, pressure, and contamination. Small imbalances can cascade into system-wide failures. Correcting these imbalances often requires interventions that create new problems. Radiation exposure further complicates stability. Outside Earth's magnetic field, radiation damages both living tissue and electronics. Shielding reduces exposure, but cannot eliminate it entirely. Over time, cumulative damage increases failure rates and health risks. Repairing radiation-damaged components often requires replacement rather than restoration, increasing dependency on supply chains. Psychological stability is also part of system stability. Long-term confinement alters behavior, decision-making, and group dynamics. Stress affects attention, memory, and impulse control. Conflicts escalate faster in environments with no escape and limited privacy. These effects feed back into system performance as maintenance lapses, communication breaks down, and procedures are bypassed. The assumption that closed systems can be perfected misunderstands how complex systems behave. Stability is not a permanent state. It is an ongoing process that requires constant energy input, oversight, and correction. On Earth, that process is distributed across planetary-scale systems that evolved over billions of years. In artificial environments, it must be actively managed by finite human and technological resources. Eventually, drift outpaces correction. Maintenance demands exceed capacity. Failures become more frequent. Recovery times lengthen. At some point, the system crosses a threshold where stability can no longer be restored. This threshold may arrive gradually or suddenly, but it is inevitable over long enough timescales. Closed systems also suffer from an often underestimated problem: invisible coupling between subsystems. In theory, air processing, water recycling, waste management, energy production, and temperature regulation can be treated as separable modules. In reality, they are deeply interdependent. A change in humidity alters microbial growth. Microbial shifts affect air chemistry. Air chemistry influences corrosion rates in mechanical components. Corrosion increases particulate contamination, which stresses filtration systems. Each subsystem appears manageable in isolation, but together they form feedback loops that amplify instability. These couplings become more dangerous over time because they are rarely fully understood during design. Engineers model expected interactions, but real systems exhibit emergent behavior. Small deviations compound through pathways that were never anticipated. On Earth, such emergence is dampened by scale and diversity. In closed habitats, emergence accelerates failure. Another limitation arises from the need for continuous optimization. Closed systems cannot remain static. Filters must be cleaned or replaced. Biological populations must be managed. Chemical concentrations must be adjusted. Each intervention slightly alters system dynamic. Over time, the system drifts further from its original configuration. The more intervention required, the faster this divergence occurs. Resource margins shrink as systems age. Consumables degrade. Zapas components are used. Zapas manufacturing capacity becomes constrained. Redundancy decreases not because it was poorly designed, but because it is gradually consumed. Once redundancy falls below a threshold, failure becomes abrupt rather than gradual. Closed systems also struggle with error recovery. On Earth, recovery often involves bringing in external expertise, materials, or energy. In isolation, recovery options are limited to what exists inside the system at that moment. A failure that would be routine on Earth becomes catastrophic when no external reset is available. The requirement for continuous vigilance imposes cognitive load on human operators. Over years or decades, constant monitoring leads to attention fatigue. Procedures become informal. Shortcuts emerge. These behaviors are not moral failures, but predictable human responses to sustained stress. Closed systems demand perfection from operators who cannot sustain it indefinitely. Even automation does not eliminate this burden. Automated systems require oversight, calibration, and maintenance. When automation fails, it often fails in opaque ways that are harder to diagnose than human error. Recovery becomes slower and more uncertain, particularly when expert knowledge has degraded. Entropy provides the final constraint. Every closed system moves toward disorder unless energy is continuously applied. While energy can delay entropy, it cannot reverse it indefinitely. Over long timescales, losses accumulate. Efficiency declines. Control margins narrow. Eventually, the system reaches a state where the energy required to maintain order exceeds what can be safely generated or managed. This is not pessimism. It is thermodynamics applied to human habitats. Closed systems can work impressively well for defined periods. They can support missions, research, and exploration. But permanence requires a level of stability that closed systems cannot provide over generational timescales. The longer a system is expected to function, the more assumptions it must uphold without violation. Over centuries, the probability that all assumptions remain valid approaches zero. Failure becomes statistically inevitable regardless of initial design quality. This is the central limitation of closed habitats. They do not fail because engineers are insufficiently skilled. They fail because complexity, time, and entropy converge. The system does not need a single catastrophic event. It only needs to keep operating long enough. This reality undermines the idea of permanent off-world habitation. Short missions are possible. Extended stays may be achievable with continuous support. But independent, self-sustaining civilizations operating in closed systems face a fundamental problem. Over time, drift is unavoidable, and failure becomes a matter of when, not if. Understanding this limitation reframes the vision of becoming multi-planetary. The challenge is not reaching another world. It is sustaining complex life in environments that lack the open-ended resilience of Earth's systems. And this leads to the next constraint, which emerges not from engineering limits, but from the biology of the humans who would have to live inside these systems. Human biology is earthbound. Even if closed systems could be stabilized and scaled, another constraint remains that technology cannot redesign away. Human biology evolved entirely within Earth's environmental envelope. Every major physiological system depends on conditions that only Earth provides consistently, and deviations from those conditions produce cascading effects that become more severe over time. Gravity is the most obvious example. Human skeletal structure, muscle mass, cardiovascular function, and even organ placement are adapted to Earth's gravitational pull. In reduced gravity environments, bone density declines measurably within months. Muscles atrophy despite intensive exercise regimens. The heart weakens as it no longer works against gravity to circulate blood. These changes are not superficial. They alter fracture risk, mobility, endurance, and long-term health. Short-duration space missions demonstrate that some effects are partially reversible upon return to Earth. That reversibility creates a false sense of confidence. It assumes Earth remains available as a recovery environment. In permanent off-world settlements, there is no return baseline. The body adapts to reduced gravity in ways that may become irreversible across generations. Children born and raised in low gravity may never develop Earth-compatible physiology at all. Radiation exposure introduces an even more serious biological constraint. Outside Earth's magnetic field and dense atmosphere, humans are exposed to higher levels of cosmic rays and solar particles. These forms of radiation damage DNA, increase cancer risk, impair neurological function, and degrade reproductive health. Shielding can reduce exposure, but it cannot replicate planetary-scale protection. Over decades, cumulative damage becomes unavoidable. Mars exemplifies this problem clearly. The planet lacks a global magnetic field, and has only a thin atmosphere. Surface radiation levels are several times higher than on Earth. Even underground habitats provide limited protection. Long-term exposure increases the probability of cancer and degenerative disease in ways that cannot be eliminated through medicine alone. Prevention becomes statistical rather than absolute. The immune system also responds poorly to space environments. Studies show altered immune responses in microgravity, including reduced effectiveness against pathogens and increased inflammatory reactions. Combined with confined living conditions, this creates heightened vulnerability to infections. Pathogens that would be manageable on Earth can spread rapidly and unpredictably in isolated populations. Vision changes observed in astronauts illustrate another systemic effect. Fluid shifts toward the head in microgravity increase pressure inside the skull, altering eye shape and impairing vision. These changes persist in some individuals long after returning to Earth. The underlying mechanisms are still not fully understood, making long-term mitigation uncertain. Reproductive biology presents perhaps the most underexplored risk. Mammalian reproduction evolved under Earth gravity, radiation levels, and circadian rhythms. Disruption of these conditions affects hormone regulation, embryonic development, and fetal growth. Animal studies conducted in space environments show increased rates of developmental abnormalities. Human data remains limited precisely because the risks are considered ethically unacceptable to test extensively. Circadian rhythm disruption compounds these issues. Earth's 24-hour day regulates sleep cycles, hormone production, and metabolic processes. On Mars, the day is longer. In space habitats, artificial lighting must substitute entirely. Even small deviations in light exposure patterns affect sleep quality, cognitive performance, and mental health. Over time, chronic circadian disruption increases risk of cardiovascular disease, depression, and impaired immune function. Nutrition cannot fully compensate for these stresses. Diets can be optimized, supplements added, and exercise protocols enforced. These measures slow degradation but do not prevent it. The body responds to environmental signals at cellular levels that technology cannot override completely. Adaptation occurs, but adaptation does not necessarily preserve health. Psychological stress feeds back into biological vulnerability. Chronic stress alters hormone balance, suppresses immune function, and accelerates aging processes. Isolation, confinement, and lack of environmental variation amplify stress responses. Even highly trained individuals experience cognitive decline and emotional instability over long durations in constrained environments. These biological effects interact. Bone loss increases fracture risk, which becomes more dangerous in environments with limited medical capability. Radiation-induced mutations interact with weakened immune surveillance. Cardiovascular deconditioning increases vulnerability to sudden exertion or emergency response. The system does not fail in one place. It erodes across many fronts simultaneously. Crucially, none of these problems disappear with time. They intensify. Human bodies do not gradually adapt toward optimal function in hostile environments. They adapt toward survival under constraint, often at the expense of long-term health and capability. Evolution operates across generations, not lifetimes, and even then requires stable reproductive populations under selective pressure. Off-world settlements lack the scale, time, and stability for such adaptation to occur safely. Another critical limitation emerges when human biology is examined not just as a collection of systems, but as an integrated whole. Physiological systems do not degrade independently. Changes in one system alter others through feedback pathways that amplify stress. Reduced bone density affects calcium regulation, which influences neural signaling and muscle function. Cardiovascular deconditioning alters blood flow patterns, affecting oxygen delivery to tissues already stressed by radiation exposure. These interactions compound risk rather than remaining isolated. Long-term studies of astronauts reveal that recovery after spaceflight is incomplete even after relatively short missions. Some individuals experience persistent neurological symptoms, cardiovascular irregularities, or immune dysfunction years later. These lingering effects suggest that biological damage accumulates faster than repair mechanisms can compensate, especially when exposure is continuous rather than episodic. Low gravity also alters fluid dynamics within the body. Blood and lymphatic circulation evolved under constant gravitational load. In microgravity or partial gravity, fluid redistribution contributes to increased intracranial pressure, kidney stone formation, and altered kidney function. These changes stress regulatory systems that already operate near biological limits. Hormonal regulation becomes unstable in off-world environments. Stress hormones remain elevated for longer periods. Melatonin production becomes irregular. Disruptions in thyroid and adrenal function affect metabolism, mood, and energy regulation. These shifts interact with sleep disruption and psychological strain, creating cycles that are difficult to interrupt once established. Medical intervention cannot fully compensate for these systemic shifts. Pharmaceuticals rely on predictable absorption, metabolism, and clearance pathways. In altered gravity and radiation environments, these pathways behave differently. Dosage effectiveness becomes less reliable. Side effects increase. Emergency medical procedures become more difficult due to fluid behavior, sterilization challenges, and equipment limitations. Genetic damage represents another accumulating risk. Even low levels of radiation exposure produce DNA mutations over time. While cellular repair mechanisms correct many errors, some persist. As mutations accumulate, cancer risk increases and cellular function degrades. In small populations, genetic damage compounds across generations, reducing overall resilience. Reproductive health faces both physiological and developmental challenges. Hormonal instability affects fertility rates. Radiation exposure increases the risk of developmental abnormalities. Limited genetic diversity in isolated populations increases susceptibility to inherited disorders. Correcting these issues would require population sizes and medical capabilities that off-world settlements cannot sustain. Aging accelerates under chronic stress. Telomere shortening, oxidative damage, and inflammation increase in constrained environments. Even with optimal nutrition and exercise, aging-related decline occurs earlier and progresses faster. This reduces the productive lifespan of individuals precisely where every skilled person is critical to system survival. The biological cost of living off-world is not evenly distributed. Some individuals tolerate stress better than others, but population-level planning cannot rely on outliers. Settlements must function based on average human performance, not exceptional resilience. As average health declines, system reliability declines with it. Children born into such environments would face unknown developmental challenges. Bone growth, organ maturation, and neural development depend on environmental cues that differ significantly from Earth conditions. Even small deviations during development can produce lifelong impairment. Over time, biological degradation feeds directly into system instability. Reduced physical capacity limits maintenance work. Cognitive decline affects decision-making. Increased illness strains medical resources. Each biological weakness increases the likelihood of technical failure, creating a reinforcing loop between human vulnerability and system fragility. These effects do not represent temporary adjustment costs. They represent a steady erosion of biological capacity. The longer humans remain outside Earth's environment, the further they move from the conditions that support long-term health. This reality places a hard boundary on the duration and scale of off-world human presence. Biology imposes constraints that technology cannot bypass without fundamentally altering what it means to be human. The implication is uncomfortable but unavoidable. Permanent human presence beyond Earth does not fail because of rockets, funding, or ambition. It fails because the human body itself is tuned to a planetary environment that cannot be reproduced elsewhere. And this biological constraint feeds directly into the final overarching limitation that ties every previous barrier together. Dependence never disappears, it only moves. All previous barriers converge on a single outcome that undermines the multi-planetary idea at its core. Even if humanity establishes settlements beyond Earth, those settlements never become truly independent. Dependence does not disappear. It simply shifts location, form, and vulnerability. Every off-world habitat begins as an extension of Earth. Materials, technology, expertise, and planning originate here. Launch systems, mission control, training pipelines, and emergency response capabilities all remain Earth-based. Early settlements rely completely on resupply and oversight. That dependence is not temporary. It becomes structural. The assumption is that, over time, settlements will bootstrap independence. Local manufacturing will replace imports. Knowledge will be transmitted and expanded locally. Infrastructure will reach self-sufficiency. History suggests otherwise. Complex systems rarely become independent through isolation. They become fragile. Consider manufacturing. Producing advanced technology requires more than raw materials. It requires ultra-pure chemicals, precision tools, clean room environments, and quality control systems refined over decades. Earth's industrial base exists because millions of interconnected facilities support one another. Replicating that depth of capability elsewhere would require recreating an entire planetary economy, not a colony. Even basic maintenance exposes the dependency problem. Machines fail unpredictably. Some failures can be repaired locally. Others require specialized components or expertise. When those components are unavailable, workarounds degrade performance. Over time, degradation accumulates. The settlement becomes less capable, not more. Medical dependence follows the same pattern. Advanced care relies on imaging equipment, pharmaceuticals, surgical tools, and specialists trained over many years. Stockpiles expire. Equipment fails. Training new specialists requires mentors and institutional continuity. Without Earth-level population size and infrastructure, medical capability inevitably contracts. Knowledge preservation is another silent dependency. Scientific understanding is not static. It requires continual validation, peer review, experimentation, and correction. Isolated knowledge systems drift toward error. Misunderstandings persist longer. Bad practices become normalized. Earth-based science works because errors are diluted across massive competitive networks. Isolation removes that corrective pressure. Economic systems also resist independence. A settlement must either trade or stagnate. Trade requires transport capacity, surplus production, and external partners. If Earth remains the only viable partner, then the settlement is not independent. If trade collapses, specialization collapses with it. The economy simplifies, reducing resilience. Political independence does not resolve material dependence. Governance structures cannot manufacture spare parts or treat radiation-induced cancers. Decisions may be local, but consequences remain tied to Earth-based support. Political autonomy without material autonomy increases risk rather than reducing it. Distance worsens every dependency. Communication delays limit coordination. Emergency response windows close. Decision-making becomes slower and less informed. Earth cannot intervene rapidly, yet remains essential. The settlement exists in a state of delayed vulnerability. This creates a paradox. The more distant the settlement, the more dependent it becomes on Earth's long-term stability. Any major disruption on Earth reverberates outward. War, economic collapse, climate failure, or technological regression on Earth would strand off-world populations with no capacity to compensate. This dependency is asymmetric. Earth can survive without off-world settlements. Off-world settlements cannot survive without Earth. That asymmetry defines the relationship permanently. A truly multiplanetary species would require multiple planets capable of mutual support. No candidate world offers that capacity. Some propose artificial intelligence as a solution. Automation could reduce human vulnerability and maintain systems indefinitely. This shifts dependence rather than eliminating it. Automated systems require maintenance, updates, and oversight. Software errors compound silently. Hardware degrades. Artificial intelligence does not escape physical constraints. Others argue that independence emerges gradually. This ignores entropy. Systems do not improve automatically with time. They require continuous investment. Earth provides that investment through population scale, diversity, and redundancy. Off-world environments cannot. The result is a network of outposts, permanently tethered to a single planetary system. This is not a distributed civilization. It is a centralized one, stretched thin. Stretching increases exposure. It does not reduce it. Dependence also manifests through decision-making authority, even when formal governance is local. Strategic planning, long-term research priorities, and technological standards are inevitably shaped by Earth-based institutions. Funding models, regulatory frameworks, and engineering norms originate on Earth and propagate outward. Off-world settlements adopt these frameworks not because they are optimal locally, but because alternatives require resources and legitimacy that isolated populations lack. Infrastructure replacement cycles further entrench dependency. Power systems, habitat structures, and life support components are designed with finite lifespans. On Earth, replacement is routine. Old systems are dismantled and new ones installed using mature supply chains. Off-world, replacement becomes a major event requiring years of preparation. Delays increase risk. Design compromises accumulate. Infrastructure ages faster than it can be renewed. Cultural dependence also emerges over time. Education systems, professional standards, and technical languages evolve on Earth. Off-world populations inherit these systems but struggle to update them independently. As divergence grows, compatibility problems arise. Tools, procedures, and assumptions no longer align perfectly with Earth-based updates. The settlement falls behind technologically without realizing it immediately. Emergency preparedness reveals the sharpest edge of dependence. Earth-based civilization assumes that catastrophic events are localized. When disasters occur, unaffected regions provide assistance. Off-world settlements lack unaffected regions. A fire, pressure breach, or power failure threatens total collapse. Preparedness plans depend on redundancy and zappers capacity that are difficult to maintain without Earth support. Supply chain compression further increases fragility. To reduce transport mass, settlements minimize inventories. This increases efficiency but reduces buffer capacity. Unexpected demand spikes or component failures exhaust reserves quickly. Reordering supplies involves months or years of delay. What would be a logistical inconvenience on Earth becomes an existential crisis off-world. Training pipelines illustrate another constraint. Skilled professionals are not interchangeable. Engineers, surgeons, material scientists, and systems operators require years of education and supervised experience. Training new experts locally requires experienced mentors, stable institutions, and access to evolving knowledge. Small populations struggle to sustain this cycle. Expertise thins over generations. Attempts to modularize civilization encounter limits. Modular systems simplify deployment but concentrate risk. A failure in a module disables all functions dependent on it. Earth mitigates this risk through diversity and redundancy across vast spaces. Off-world settlements concentrate functions into minimal volumes, increasing coupling and reducing fault tolerance. Legal and ethical systems also rely on Earth. Medical ethics, research standards, and safety thresholds are defined within Earth-based contexts. Off-world environments challenge these standards in unforeseen ways. Deviations become necessary but lack external validation. Over time, ethical drift mirrors technical drift, with consequences that may only become apparent after harm occurs. The concept of mutual aid between settlements is often proposed as a path toward independence. This assumes multiple viable settlements exist simultaneously. In reality, early settlements will be few, small, and widely separated. Transport between them is more difficult than transport to Earth. Mutual support remains theoretical rather than practical. Dependence also constrains innovation. Risk-taking decreases when failure carries irreversible consequences. Settlements prioritize stability over experimentation. Earth-based innovation accelerates through trial, error, and failure. Off-world environments cannot tolerate the same failure rates. Technological progress slows, increasing reliance on Earth-based advances. Over time, these factors converge into a stable but fragile state. The settlement survives only as long as Earth remains capable and willing to support it. Independence never arrives because the conditions required for independence require independence to already exist. This is not a flaw of planning or commitment. It is an emergent property of complex systems operating under extreme constraint. Dependence does not vanish, it migrates into deeper layers of operation, becoming harder to see and harder to resolve. This reframes the meaning of becoming multiplanetary. The issue is not whether humans can live somewhere else for a while, they can. The issue is whether civilization can exist without Earth as its anchor. Every line of evidence points in the same direction. Earth is not just humanity's origin, it is humanity's operating system. Removing that system does not produce independence. It produces fragility. And fragility, when extended across interplanetary distances, becomes terminal. The remaining question is not why humanity has not become multiplanetary yet. It is whether the concept itself misunderstands what makes civilization possible in the first place. Time works against expansion, not for it. A common assumption behind multiplanetary thinking is that time is an ally. The longer humanity works on space settlement, the argument goes, the closer it will come to solving every limitation. History suggests the opposite. Over long durations, complex projects do not become easier. They become more constrained, more expensive, and more fragile as external pressures accumulate. Civilizations do not progress along smooth, uninterrupted curves. They rise, stabilize, fragment, and sometimes regress. Every long-term technological effort on Earth has been shaped by political shifts, economic cycles, resource scarcity, and social change. Space programs are not exempt from these forces. They are especially vulnerable to them because they depend on sustained coordination across generations. Becoming multiplanetary is not a one-time achievement. It is a permanent commitment. Habitats must be maintained, upgraded, defended, and supported indefinitely. Any interruption compounds risk. A single decade of reduced funding, disrupted governance, or technological stagnation can undermine systems that took generations to build. Earth-based infrastructure can survive pauses and recover. Off-world systems cannot. Time also increases exposure to rare but inevitable events. The longer a settlement exists, the higher the probability that it encounters a critical failure. This could be a medical crisis, a systems malfunction, a supply disruption, or an environmental anomaly. Even if the probability of failure in any given year is low, cumulative risk grows steadily. Over decades or centuries, failure becomes statistically inevitable. Technological optimism often ignores maintenance realities. Technologies age, materials fatigue, software becomes obsolete. Knowledge gaps emerge as original designers retire or die. Earth-based systems absorb these effects through replacement and redundancy. Off-world systems must carry their entire maintenance burden locally or rely on delayed external support. Energy infrastructure illustrates this problem clearly. Power systems degrade over time. Solar panels lose efficiency. Nuclear systems require refueling, inspection, and waste handling. Each maintenance cycle introduces risk. Delaying maintenance increases failure probability. Accelerating maintenance increases resource strain. Time turns every system into a balancing act with narrowing margins. Political continuity is another hidden variable. Long-term space settlement assumes stable governance and sustained public support across centuries. No civilization has demonstrated that level of continuity. Political priorities shift. New crises emerge. Resources are reallocated. Commitments made by one generation are abandoned by the next. Earth-based populations adapt. Off-world settlements are left exposed. Cultural drift compounds this instability. Isolated populations develop divergent values, norms, and priorities. Over time, these differences affect decision-making and risk tolerance. Policies optimized for Earth may be ignored or reinterpreted. Coordination breaks down. The settlement becomes less aligned with the systems it depends on. Time also magnifies environmental mismatch. human adaptation to non-Earth environments does not necessarily improve long-term viability. Physiological changes that support short-term survival can reduce overall resilience. Technological adaptations designed for current conditions may fail as environments change. Mars dust storms, solar activity cycles, and orbital variations introduce long-term variability that systems must accommodate indefinitely. Resource depletion is another temporal constraint. Local resources assumed to be sufficient may not be. Extraction rates may exceed replenishment. Processing may introduce contaminants. Waste accumulation may reach critical thresholds. Earth's ecosystems evolved mechanisms to handle these pressures over geological time. Artificial systems have no such legacy. Even communication degrades with time. Hardware ages. Protocols change. Institutional memory fades. The longer a settlement exists, the harder it becomes to maintain alignment with Earth-based systems. Delays increase. Errors propagate. Coordination costs rise. The belief that future technology will solve these problems assumes uninterrupted progress. History does not support that assumption. Technological development is uneven and contingent. Breakthroughs are unpredictable. Dependencies shift. Solutions introduce new vulnerabilities. Time also alters risk perception. Early settlers may accept extreme risk willingly. Later generations did not choose those conditions. They inherit them. Over time, tolerance for risk declines while system fragility increases. This mismatch creates internal pressure that undermines cohesion. The result is a long-term trend toward contraction rather than expansion. Systems simplify to survive. Capabilities are abandoned. Dependency increases. The settlement becomes an outpost, not a civilization. This is not a failure of imagination. It is a consequence of how complex systems behave over time. Expansion amplifies exposure. Duration amplifies fragility. Earth survives these pressures because it is vast, diverse, and self-regulating. Off-world environments are none of these. Time, often portrayed as the solution, becomes the silent force that erodes every assumption behind becoming multiplanetary. And this erosion leads directly to the final constraint, one that is not technical, biological, or political, but structural in the deepest sense. Civilization is not portable. At this point, the limitations converge into a more fundamental realization. Civilization itself is not something that can be packed, transported, and reassembled elsewhere. It is an emergent property of scale, density, history, and environment. When people talk about humanity becoming multiplanetary, they often imagine moving civilization the way one might move a city. In reality, civilization is inseparable from the conditions that allowed it to form. Civilization depends on layers of infrastructure built on top of one another over long periods of time. Roads, ports, power grids, communication networks, education systems, legal frameworks, scientific institutions, and cultural norms all interact continuously. These layers evolve together under Earth's conditions. They are not modular components that function independently. Removing one layer destabilizes others. Attempting to rebuild all layers simultaneously in a hostile environment multiplies risk rather than reducing it. Economic complexity illustrates this clearly. Modern civilization relies on deep specialization. Individuals focus on narrow roles while depending on vast networks to meet their needs. This specialization only works when population size, resource availability, and logistical capacity exceed certain thresholds. Below those thresholds, economies simplify. Specialization collapses. People are forced to perform multiple roles inefficiently. Productivity declines, not because of incompetence, but because the system cannot sustain complexity. Historical examples support this pattern. Isolated settlements on Earth often regress technologically despite access to known techniques. Knowledge was lost because there were too few practitioners to maintain it. Tools degraded without replacement. Skills became ceremonial rather than functional. This occurred even in environments far more forgiving than Mars or space habitats. Legal and governance systems also depend on scale. Laws require enforcement. Enforcement requires institutions. Institutions require trained personnel, legitimacy, and resources. In small, isolated populations, governance becomes informal and brittle. Disputes escalate faster. Authority is harder to maintain. Long-term planning gives way to short-term survival decisions. Science itself depends on civilization-scale interaction. Progress requires peer review, replication, debate, and error correction across large communities. Isolated scientific efforts drift towards stagnation or error. Even well-intentioned researchers benefit from competition and critique. Remove that ecosystem and science becomes fragile. Cultural continuity is equally vulnerable. Traditions, language, and shared values evolve through constant interaction with diverse groups. Isolation accelerates divergence. Over generations, cultures become inward-focused. Innovation slows. Social norms harden. Adaptability declines. The idea that technology alone can compensate for these losses misunderstands what technology represents. Technology is not just hardware. It is embedded knowledge, training systems, and cultural practices. A machine without a supporting ecosystem becomes unusable once it fails. Software without ongoing development becomes obsolete. Knowledge without institutions erodes. Transport limitations reinforce this reality. Moving people is easier than moving systems. A single spacecraft can carry humans. It cannot carry the invisible networks that sustain them. Each off-world settlement starts stripped of these networks and must rebuild them under far worse conditions than those on Earth. The problem compounds across generations. First settlers rely on Earth heavily. Second generations inherit systems already under strain. Third generations face diminishing capability unless support increases. Independence moves further away with time, not closer. This does not mean humans cannot survive beyond Earth temporarily. It means survival is not the same as civilization. A small population living under constant constraint is not a second civilization. It is an outpost. Understanding this distinction clarifies why becoming multiplanetary is not a matter of reaching another world. It is a matter of reproducing the conditions that allow civilization to exist at all. And those conditions appear to be extraordinarily rare. This leads to the final realization that ties every constraint together. The obstacle is not one factor, it is the interaction of many. Earth provides a unique alignment of conditions that civilization requires simultaneously. Remove anyone and strain increases. Remove several and collapse becomes likely. The idea of becoming multiplanetary persists because it appeals to survival instinct and technological optimism. But when examined through the lens of systems, biology, scale, time, and civilization itself, it begins to look less like a future destination and more like a misunderstanding of what humanity actually is. The remaining chapters will not introduce new barriers so much as trace how all of these constraints reinforce one another. Because the reason humanity may never become truly multiplanetary is not hidden in some unknown variable. It is visible in the structure of civilization itself. Redundancy cannot be created from scarcity. One of the most misunderstood concepts in discussions about space settlement is redundancy. On Earth, redundancy is so pervasive that it becomes invisible. Food systems overlap. Energy grids back one another up. Medical care is distributed across regions. If one system fails, another absorbs the shock. Civilization survives not because failures do not occur, but because failures rarely propagate unchecked. Beyond Earth, this fundamental property disappears. Redundancy requires surplus. It requires more resources, more infrastructure, and more capacity than is immediately necessary. Earth has this surplus because it operates at planetary scale. Multiple agricultural regions produce food. Multiple nations generate energy. Multiple institutions train specialists. This excess is inefficient in the short term, but essential in the long term. It allows systems to fail without collapsing the whole. Off-world environments operate at the opposite extreme. Every resource is constrained. Every kilogram launched carries cost. Every additional system adds complexity and risk. As a result, designs are optimized for efficiency rather than resilience. Components are shared across functions. Margins are minimized. Redundancy is reduced wherever possible to save mass, energy, and space. This creates a fragile equilibrium. When systems function as intended, the habitat survives. When something deviates, there is little capacity to absorb the deviation. Backup systems often rely on the same underlying infrastructure. A power failure affects life support, communication, and thermal regulation simultaneously. A single leak compromises atmosphere, pressure, and temperature at once. Attempts to add redundancy encounter diminishing returns. Each backup system requires its own maintenance, power supply, and spare parts. These requirements increase overall system load. At some point, adding redundancy increases the probability of failure rather than reducing it. Engineers refer to this as complexity-induced fragility. Earth avoids this trap because its redundancy is distributed. Failures are spatially separated. A drought in one region does not eliminate global food production. A blackout in one city does not disable the entire grid. Off-world habitats concentrate all functions into a single location. There is no spatial buffer. This concentration magnifies risk. Fire, structural damage, or contamination affects the entire population simultaneously. Evacuation options are limited or non-existent. On Earth, populations relocate in response to disasters. Off-world populations cannot. Redundancy also applies to human roles. Earth societies can replace individuals because skills are widespread. If one specialist is lost, another exists. In small populations, expertise is scarce. The loss of a single individual can permanently remove critical knowledge. Training replacements takes time that the system may not have. Automation does not eliminate this problem. Automated systems reduce labor requirements, but increase dependence on specialized maintenance. When automation fails, recovery becomes more difficult, not less. Software errors can affect entire systems instantly. Hardware failures propagate faster when humans are not directly involved in daily operation. Supply chain redundancy presents the same issue. Earth's supply chains are global and flexible. If one supplier fails, alternatives exist. Off-world settlements rely on narrow, rigid supply lines. Launch windows constrain timing. Manufacturing capacity is limited. Delays cascade. Environmental unpredictability worsens this vulnerability. Dust storms, radiation spikes, thermal extremes, and material degradation introduce random stressors. Redundant systems designed for expected conditions may fail under unexpected ones. Earth's ecosystems evolved to handle variability. Artificial systems did not. Over time, redundancy erodes further. Components wear out, spares are consumed, systems are repurposed. What began as a redundant design becomes a single point of failure system through necessity rather than negligence. This erosion is not the result of poor planning. It is the result of operating in scarcity. When resources are limited, redundancy competes with survival. Survival wins. The implication is stark. Civilization relies on redundancy to persist through uncertainty. Off-world environments cannot provide redundancy at the required scale. Without it, systems become brittle. Brittle systems do not tolerate long timelines. As this pattern repeats across life support, energy, medicine, knowledge, and governance, it reinforces a consistent outcome. Expansion does not increase resilience, it redistributes vulnerability. This reality reframes the ambition of becoming multi-planetary. It is not simply about reaching another world, it is about sustaining redundancy under constraint, and every attempt to do so reveals the same structural problem. Redundancy cannot be created from scarcity. It emerges only where surplus exists. Earth provides that surplus naturally. Beyond Earth, scarcity is the defining condition. Risk does not average out, it compounds. A common justification for becoming multiplanetary is risk distribution. The argument assumes that spreading humanity across multiple locations reduces the chance of total collapse. This logic works for systems that are independent and loosely coupled. Human civilization is neither. When examined closely, off-world expansion does not distribute risk evenly, it compounds it. Risk averaging only functions when failures in one location do not affect others. Earth-based cities meet this condition. A flood in one region does not trigger floods elsewhere. A power failure in one country does not shut down global infrastructure. The key is independence. Off-world settlements lack it. Every off-world population remains tied to Earth through material, informational, and institutional dependence. Failures on Earth propagate outward. A launch system failure affects all settlements simultaneously. Economic collapse disrupts supply chains universally. Political conflict halts coordination. Earth remains a single point of failure. At the same time, off-world settlements introduce new failure modes that Earth does not share. Radiation exposure, habitat breaches, life support instability, and long-term isolation are risks unique to space environments. These risks do not replace Earth-based risks. They stack on top of them. This stacking effect creates asymmetric exposure. Earth must remain stable for off-world settlements to survive, while off-world settlements add no meaningful protection for Earth. In probabilistic terms, total system risk increases. Humanity becomes exposed to more failure pathways without removing existing ones. Compounding risk also arises from synchronization. Many off-world systems depend on the same technologies, suppliers, and expertise. A flaw in a widely used design affects multiple settlements simultaneously. This is not diversification, it is replication of vulnerability. Space infrastructure amplifies this problem. Launch vehicles, navigation systems, communication networks, and life support technologies are standardized to reduce cost and complexity. Standardization increases efficiency, but reduces resilience. A systemic flaw propagates everywhere at once. Distance worsens response times. When failures occur off-world, corrective action is delayed by physics. Communication delays limit diagnosis. Transport delays limit intervention. The longer the delay, the more likely the failure becomes irreversible. Risk also compounds over time. Each additional settlement adds maintenance burden, monitoring requirements, and coordination complexity. Attention is finite. Resources are finite. As commitments expand, margins shrink. Small oversights become consequential. Psychological factors further distort risk management. Success biases decision-making. Early survival reinforces optimism. Warning signs are discounted. Systems appear stable until they fail abruptly. This pattern appears repeatedly in complex technological disasters on Earth. Off-world environments reduce tolerance for error. On Earth, errors are localized. In space, errors cascade. A misjudgment that would be recoverable on Earth becomes fatal in isolation. This shifts risk from gradual to catastrophic. The belief that humanity can outrun existential risk by expansion misunderstands the nature of systemic failure. Collapse does not require simultaneous failure everywhere. It requires failure at critical nodes. Earth remains that node. Adding off-world populations increases operational surface area. More systems to monitor, more environments to manage, more failure points to defend. Without independence, this expansion stretches resilience thinner rather than spreading it wider. This leads to a counterintuitive conclusion. From a systems perspective, consolidation on Earth reduces risk more effectively than expansion. Earth's redundancy, repair capacity, and adaptability absorb shocks that would annihilate isolated settlements. The idea that risk naturally averages out across planets assumes a statistical independence that does not exist. All settlements share the same technological lineage, biological constraints, and central dependencies. Failures correlate. Risk management is not about adding locations, it is about reducing coupling. Off-world expansion increases coupling across longer distances under harsher conditions. This realization reframes the original motivation behind becoming multi-planetary. The strategy does not reduce existential risk. It reorganizes it into a more complex and fragile configuration. What remains is not a distributed civilization, but a stretched one. and stretched systems, as history shows, do not fail gracefully. Independence requires conditions that do not exist. At this stage, the idea of independence becomes the central assumption that must be tested. Multi-planetary thinking depends on the belief that off-world settlements will eventually reach a point where they no longer rely on Earth. Once that threshold is crossed, the argument goes, humanity will have secured its future. The problem is that the conditions required for true independence do not appear to exist anywhere beyond Earth. Independence is not merely the ability to survive. It is the ability to absorb shocks, adapt to change, and recover from failure without external rescue. On Earth, this capability emerges from diversity. Diverse climates, diverse resources, diverse populations, and diverse institutions create resilience. When one region fails, another compensates. This structure does not exist on other planets. Mars, often presented as the best candidate for settlement, lacks the basic ingredients for independence. Its atmosphere is thin and unstable. Its surface radiation levels are high. Liquid water is scarce and difficult to access. Its soil contains toxic compounds that complicate agriculture. Every solution to these problems relies on imported technology and constant maintenance. None scale naturally. Even if infrastructure is established, independence requires redundancy across every critical domain. Energy production must continue under all conditions. Food systems must withstand disease, failure, and environmental variation. Medical care must address both routine and catastrophic needs. Education must train new specialists. Governance must manage conflict and uncertainty. Industry must replace worn equipment. None of these domains can be sustained indefinitely by small, isolated populations. Population size is the defining constraint. Independence requires millions of people to support specialization, innovation, and redundancy. Smaller populations collapse into generalism, where individuals perform multiple roles imperfectly. Productivity declines, safety margins shrink. Over time, capability contracts. Expanding population introduces new problems. Resource consumption increases. Waste accumulates. Infrastructure strain grows. Earth's ecosystems evolved mechanisms to manage these pressures. Artificial environments did not. Growth accelerates failure rather than independence. Local resource extraction is often cited as the solution. In theory, mining asteroids or planetary crusts could supply raw materials. In practice, extraction requires heavy equipment, energy, and processing capacity. Each step introduces complexity and risk. The initial infrastructure to enable extraction must still be imported. Manufacturing presents an even greater challenge. Producing advanced components requires precision environments, supply chains, and quality control. Earth's manufacturing ecosystems took centuries to develop. Attempting to compress that process into a hostile environment with limited population and resources is not realistic. Knowledge systems cannot be isolated either. Scientific progress depends on collaboration, competition, and verification across large communities. Small, isolated research groups stagnate. Errors persist longer. Innovation slows. Over generations, technical capability declines rather than improves. Environmental unpredictability further undermines independence. Dust storms, radiation fluctuations, and orbital variations introduce stressors that require adaptive capacity. Earth's biosphere absorbs variability naturally. Artificial systems require active intervention for every deviation. Medical independence illustrates the human cost of this limitation. Rare diseases, complex injuries, and chronic conditions require specialized treatment. A settlement cannot stock every medication, tool, or specialist. Earth-based medicine relies on scale and redundancy. Isolation eliminates both. True independence also requires political and social stability across generations. Small, confined populations experience heightened conflict and social strain. Governance becomes more brittle. Dissent has fewer outlets. Over time, instability undermines institutional continuity. The assumption that independence emerges naturally with time reverses historical patterns. Independence requires favorable conditions first. Time alone does not create them. In hostile environments, time erodes capacity rather than building it. This leads to a hard conclusion. There is no threshold beyond which an off-world settlement becomes self-sustaining in the way Earth is. There is only a sliding scale of dependence, with independence always out of reach. This does not mean humanity cannot expand its presence temporarily. It means that permanent independence beyond Earth remains incompatible with the conditions available, and this incompatibility becomes even clearer when examined through the lens of resources, which introduces the next constraint. Resources do not behave the way models assume. Discussions of off-world settlement often rely on resource models that appear neat and reassuring on paper. Charts show estimated water content, mineral abundance, and energy potential. These models create the impression that once humans reach another planet, resources will simply be unlocked through effort and engineering. In practice, resources rarely behave the way projections suggest, especially in environments where every extraction step carries risk. On Earth, resources are accessible because geological processes concentrated them over billions of years, and because ecosystems help manage byproducts. Even so, extraction is costly, environmentally disruptive, and politically complex. Beyond Earth, resources are harder to reach, harder to process, and far less forgiving of error. Take water, often described as abundant on Mars in the form of ice. Ice deposits exist, but accessibility varies widely. Many are buried beneath layers of rock and dust. Extracting them requires heavy machinery, sustained energy input, and maintenance under extreme conditions. Once extracted, the water must be purified, stored, and recycled with near-perfect efficiency. Losses that would be tolerable on Earth become unacceptable over time. Energy constraints amplify this problem. Resource extraction is energy-intensive. Drilling, heating, crushing, and processing material all require reliable power. Solar energy is intermittent and vulnerable to environmental disruption. Nuclear power introduces logistical and safety challenges that compound over decades. Energy shortfalls directly limit extraction rates, creating bottlenecks that ripple across every system. Mineral availability presents a similar issue. The presence of an element does not guarantee usability. Ores must be concentrated, separated, and refined. On Earth, this is accomplished through large-scale industrial processes supported by extensive infrastructure. Off-world environments lack the gravity, atmosphere, and waste sinks that make these processes efficient. Tailings accumulate. Contaminants spread. Equipment wears rapidly. Manufacturing from local materials compounds uncertainty. Producing usable components requires consistent quality control. Variability in raw materials increases defect rates. Defects increase failure probability. Failure in closed systems has cascading consequences. Over time, the reliability gap between Earth-manufactured and locally produced components widens. Transport constraints further complicate resource use. Moving material within low-gravity environments introduces unique engineering challenges. Dust infiltration damages machinery. Abrasive particles accelerate wear. Maintenance demands increase as extraction continues. Resource depletion is often underestimated. Early models assume static availability, but extraction alters local conditions. Ice sublimates. Structural stability changes. Contamination spreads. Over time, the easiest resources are exhausted, leaving increasingly difficult deposits. This pattern mirrors Earth's experience, but without Earth's buffers. Waste management becomes an escalating problem. Extraction produces byproducts that must be contained or processed. Earth disperses waste through atmosphere, water, and biological cycles. Off-world habitats must store or recycle waste indefinitely. Accumulation increases risk and limits usable space. Political and economic assumptions further distort resource planning. Models often assume uninterrupted access and stable governance. In reality, priorities shift. Crises redirect resources. Maintenance budgets are cut. Deferred upkeep reduces efficiency and increases failure rates. The result is a widening gap between projected resource capacity and actual usable output. Systems designed around optimistic assumptions struggle to meet demand. Shortfalls propagate across food production, energy supply, and manufacturing. This is not a failure of modeling alone. It reflects a deeper misunderstanding. Resources are not just quantities. They are embedded in systems that require context to function. Earth provides that context naturally. Other environments do not. As reliance on local resources increases, vulnerability increases with it. The settlement becomes more exposed to fluctuations it cannot control. Independence moves further away, not closer. This reinforces the central pattern. Every attempt to solve one constraint intensifies another. Resources do not liberate off-world settlements. They entangle them in new dependencies and risks. Understanding this prepares the ground for the next limitation, one that operates not through scarcity, but through uncertainty itself. Uncertainty cannot be engineered away. At a certain point, the discussion stops being about known limitations and becomes about uncertainty itself. Plans for becoming multi-planetary often acknowledge risks, but they assume those risks can be bounded, quantified, and mitigated through better design. This assumption breaks down when uncertainty is not peripheral but central to the system. Complex systems fail most often not because of known problems, but because of unknown interactions. Earth's biosphere contains countless unknowns, yet it remains stable because it evolved through continuous feedback and adaptation across immense timescales. Artificial systems do not have this history. They are assembled based on incomplete understanding and operate without evolutionary buffers. Every off-world environment introduces unknown variables. Mars presents dust chemistry that interacts unpredictably with machinery and human health. Radiation profiles vary with solar cycles in ways that cannot be forecast precisely. Subsurface conditions remain partially unmapped. Even small deviations from expected conditions can have outsized consequences in closed systems. Engineering works best when variables are controlled. Space environments are defined by variables that cannot be fully controlled. Thermal fluctuations, micrometeoroid impacts, radiation storms, and material degradation introduce randomness. Redundancy can mitigate expected failures, but it cannot anticipate novel interactions. Biological uncertainty compounds this problem. Living systems adapt in ways that defy linear prediction. Microbial communities shift, mutations accumulate. Ecosystems behave differently under altered gravity and radiation. These changes may appear benign initially, only to trigger instability later. Correcting such shifts requires interventions that may create additional unforeseen effects. Human behavior introduces another layer of unpredictability. Decision-making under isolation, stress, and delayed feedback diverges from modeled assumptions. Small social tensions can escalate. Informal practices replace formal procedures. Safety margins erode gradually, often unnoticed until a critical failure occurs. Software uncertainty is equally problematic. Modern systems rely heavily on automated control. Software interacts with hardware, sensors, and human input in complex ways. Rare edge cases become inevitable over long timelines. Updates introduce new bugs. Compatibility issues emerge. In closed systems, software faults can propagate instantly. Uncertainty also grows with time. Systems drift. Environments change. Knowledge becomes outdated. Models lose relevance. The longer a settlement operates, the less its initial assumptions reflect reality. This divergence is manageable on Earth because systems can be redesigned at scale. Off-world, redesign capacity is limited. Attempts to over-engineer against uncertainty increase complexity. Complexity itself becomes a source of failure. Each added safeguard introduces new interactions. Eventually, the system becomes opaque. Operators understand it less well. Diagnosis slows. Recovery becomes harder. Earth tolerates uncertainty because it distributes it. Failures are localized. Learning occurs across populations. Errors are corrected through competition and redundancy. Off-world systems concentrate uncertainty into a single environment. When uncertainty manifests, it affects everything at once. This concentration transforms uncertainty into existential risk. Unknowns cannot be eliminated, only endured. Earth evolved to endure them. Artificial habitats did not. The belief that future knowledge will eliminate uncertainty misunderstands the nature of complex systems. Knowledge reduces some unknowns while revealing others. The boundary of uncertainty moves. It does not disappear. As settlements age, uncertainty becomes cumulative. Each unresolved deviation alters baseline conditions. Over time, the system becomes less predictable, not more. Maintenance becomes reactive. Confidence declines. Risk tolerance increases out of necessity. This reality challenges the premise that humanity can simply outthink the problem of off-world survival. Intelligence does not grant immunity to uncertainty. It often increases exposure by encouraging complexity. Understanding uncertainty as a fundamental constraint clarifies why becoming multiplanetary is not a matter of overcoming a checklist of problems. It is about confronting environments where unpredictability is the norm and correction capacity is limited. The next constraint follows naturally. When uncertainty dominates, decision-making itself becomes a liability, and that introduces the human factor in its most consequential form. Decision-making breaks under isolation. Decision-making is often treated as a purely cognitive process, something that improves with intelligence, training, and data. In reality, decision-making is deeply shaped by environment. Where humans live determines how they assess risk, respond to uncertainty, and coordinate action. Off-world environments place decision-making under conditions that steadily degrade its reliability rather than enhance it. On Earth, most decisions occur within layered support structures. Individuals rely on institutions, social norms, legal systems, and shared experience to guide judgment. Errors are corrected through feedback. Poor decisions can be challenged, reversed, or diluted by broader systems. In isolated habitats, these buffers are sharply reduced or removed entirely. Isolation alters perception first. When the same environment is experienced repeatedly without variation, cognitive narrowing occurs. Attention focuses on immediate concerns at the expense of long-term consequences. This effect has been documented in polar research stations, submarines, and confined industrial settings. Over time, risk assessment becomes distorted. Rare but catastrophic risks are discounted, while familiar inconveniences are exaggerated. Delayed feedback worsens this distortion. Off-world settlements operate with communication delays that limit real-time consultation. Decisions must be made locally, often without full information. Mistakes cannot be corrected quickly. This increases reliance on intuition rather than analysis. Intuition evolved for short-term survival in familiar environments, not for managing complex technological systems under unprecedented conditions. Group dynamics further complicate decision-making. Small populations magnify interpersonal relationships. Authority becomes personalized. Dissent carries higher social cost. Over time, groupthink emerges. Alternative viewpoints are suppressed not through malice, but through fatigue and the desire for cohesion. Safety protocols are bypassed gradually as informal practices replace formal ones. Stress acts as a continuous background influence. Chronic stress alters hormone levels, impairs memory, and reduces cognitive flexibility. Under stress, humans favor simple solutions and familiar patterns, even when inappropriate. In closed environments, stress does not dissipate. It accumulates. Leadership becomes both more critical and more fragile. Leaders in isolated settlements face constant pressure with limited support. Decision fatigue sets in. Burnout follows. Succession planning is difficult in small populations. When leadership fails, recovery options are limited. Procedural drift is another inevitable outcome. Written procedures exist to manage risk, but adherence declines over time. Small deviations become normalized if they appear to work. This process has been observed repeatedly in high-risk industries on Earth, including aviation and nuclear power. In off-world environments, the consequences are amplified. Ethical decision-making also changes under constraint. Scarcity forces trade-offs that would be unacceptable on Earth. Resource allocation decisions take on life and death significance. Over time, moral frameworks shift to accommodate survival priorities. This can erode trust and legitimacy within the group. Children raised in isolated environments inherit these conditions without choice. Their cognitive development occurs within constrained sensory and social input. This affects learning, creativity, and problem-solving in ways that are not fully understood. Education becomes narrower, innovation declines. Emergency decision-making reveals the sharpest contrast. On Earth, emergencies mobilize external resources. Off-world, emergencies consume internal capacity. Responding to one crisis weakens readiness for the next. Decision-making becomes reactive rather than strategic. The accumulation of small decision errors eventually creates systemic vulnerability. No single mistake causes collapse. Instead, a pattern emerges. Margins shrink. Recovery times lengthen. Confidence replaces caution. The system appears stable until it is not. This degradation is not a failure of character or competence. It is a predictable response to isolation, confinement, and uncertainty. Humans are adaptive, but adaptation under constraint often sacrifices long-term resilience for short-term stability. The belief that training can fully compensate for these effects ignores decades of evidence. Training improves performance temporarily. Environment shapes it permanently. Earth provides an environment that supports distributed decision-making across large populations. Off-world settlements concentrate responsibility into too few minds under too much pressure. As decision quality declines, reliance on automation increases. Automation then introduces new decision layers that humans struggle to oversee effectively. When automated systems fail, human operators are least prepared to intervene. This interaction between isolation, stress, and decision-making completes a critical loop. Systems become harder to manage just as management capacity erodes. Errors become more consequential as tolerance decreases. Understanding this limitation clarifies why becoming multiplanetary is not simply an engineering challenge. It is a human one. Decision-making does not scale down well. It degrades under isolation. And degraded decisions accelerate every other failure pathway already described. The remaining chapters will trace how these decision constraints interact with economics, governance, and long-term survival, revealing why the structure of human cognition itself resists permanent expansion beyond Earth. Economic systems cannot survive permanent constraint. Economic systems are often treated as adaptable mechanisms that will naturally reorganize themselves around new environments. In reality, economies only function when certain baseline conditions are met, and those conditions are absent in every off-world setting currently proposed. Once those conditions are removed, economic activity does not evolve upward toward complexity. It simplifies, contracts, and eventually stalls. Modern economies rely on surplus. Surplus allows specialization, trade, innovation, and error correction. On Earth, surplus emerges from scale, diversity of resources, and relative environmental stability. Agricultural systems produce more food than is immediately needed. Energy systems generate excess capacity. Labor specialization becomes viable because basic needs are met reliably. Off-world environments invert this structure entirely. In isolated habitats, nearly all economic activity is directed towards survival maintenance. Energy is consumed to maintain pressure, temperature, and air quality. Labor is consumed by repair, monitoring, and contingency planning. Resources cannot be stockpiled easily because storage introduces risk and degradation. Under these conditions, surplus does not accumulate. Without surplus, economic growth becomes structurally impossible. Trade is often proposed as the solution. Settlements could export resources, data, or manufactured goods to Earth in exchange for supplies. This model fails under scrutiny. Transport costs across interplanetary distances remain immense, even under optimistic propulsion assumptions. Launch windows limit timing. Payload mass is constrained. Any export must justify extraordinary energy expenditure. Few goods meet that threshold. Information is frequently cited as a low-mass export. Scientific data, intellectual property, or computational services could, in theory, support an off-world economy. This assumes uninterrupted communication infrastructure, competitive relevance, and sustained demand. Communication delays undermine real-time services. Specialized expertise degrades in isolation. Earth-based alternatives outperform isolated ones due to scale and collaboration. Currency itself becomes problematic. Economic systems require stable units of exchange and shared trust. In small, isolated populations, economic roles overlap heavily. Market mechanisms blur into administrative allocation. Price signals lose meaning when scarcity dominates and alternatives do not exist. What emerges resembles rationing rather than a functioning economy. Labor markets collapse under constraint. On Earth, individuals change roles, retrain, or relocate. Off-world, mobility is minimal. Training pipelines are narrow. Labor allocation becomes rigid. Inefficiencies accumulate. Burnout increases. Productivity declines despite high individual effort. Capital formation is equally constrained. Investment requires delayed returns and tolerance for risk. In survival-dominated environments, risk tolerance collapses. Every failure threatens system stability. As a result, experimentation decreases. Innovation slows. Systems become conservative by necessity. Maintenance costs steadily consume economic capacity. Infrastructure built under ideal conditions ages in hostile environments. Replacement cycles shorten. Deferred maintenance becomes tempting. Each delay increases future cost. Eventually, maintenance overwhelms productive capacity. At that point, the economy enters a negative feedback loop. Earth-based economies avoid this trap through expansion and substitution. New regions develop. New technologies replace old ones. Off-world settlements cannot expand meaningfully. Every expansion increases strain. Substitution requires manufacturing capacity that does not exist locally. Inequality emerges rapidly in constrained economies. Access to critical skills, information, or authority concentrates power. Economic roles harden into hierarchies. Social mobility declines. Discontent rises. Governance must intervene, further distorting economic signals. External shocks are particularly destabilizing. On Earth, economic shocks are buffered through diversification. Off-world, shocks propagate directly. A single supply delay affects every sector simultaneously. Recovery options are limited. The economy does not rebound. It retrenches. Generational effects deepen the problem. Early settlers may accept economic austerity willingly. Later generations inherit it without consent. Expectations diverge from reality. Motivation declines. Productivity follows. The assumption that automation resolves these constraints overlooks its economic cost. Automated systems require capital, maintenance, and energy. They reduce labor demand, but increase system fragility. When automation fails, recovery is expensive and slow. Over time, economic activity simplifies towards subsistence. Trade narrows, innovation stagnates. The settlement survives, but it does not progress. It becomes an economic endpoint rather than a growth node. This outcome is not accidental. It follows directly from operating under permanent constraint. Economies are not abstract systems that float free of environment. They are expressions of surplus, scale, and flexibility. Remove those foundations, and economic complexity collapses. Financial coordination itself becomes increasingly difficult under constraint. On Earth, economic systems rely on distributed information flows that allow participants to respond dynamically to changing conditions. Prices, wages, and investment signals adjust through constant feedback. In off-world settlements, information is limited, delayed, and filtered through administrative structures. This slows adaptation and increases misallocation of resources. Risk pooling, a foundational economic mechanism, also breaks down. Earth-based economies distribute risk across large populations and diverse industries. Insurance, credit markets, and state mechanisms absorb shocks. In isolated environments, risks are correlated. A single failure often affects every individual simultaneously. Under these conditions, traditional risk mitigation tools lose effectiveness. Entrepreneurship is similarly constrained. New ventures require capital, tolerance for failure, and access to markets. In off-world settlements, failure carries disproportionate cost. A failed experiment may consume scarce resources needed for survival. As a result, innovation shifts from exploratory to incremental. Systems optimize for reliability, not transformation. Supply chain compression introduces further inefficiencies. Earth's economies rely on just-in-time logistics balanced by global redundancy. Off-world supply chains are long, sparse, and inflexible. Delays are expected rather than exceptional. This forces over-engineering and hoarding, both of which increase resource consumption and system fragility. Resource valuation also changes under constraint. On Earth, value reflects utility, scarcity, and substitutability. Off-world, scarcity dominates. Essential resources lose price flexibility because alternatives do not exist. Allocation becomes centralized. Markets lose their coordinating function and transition toward command structures. Intergenerational economic mobility becomes limited. Education systems narrow as training focuses on immediate operational needs. Cultural and intellectual pursuits are deprioritized. This reduces creativity and long-term problem-solving capacity. Over generations, economic roles solidify, reinforcing inequality and reducing adaptability. External investment is often suggested as a stabilizing force. Earth-based entities could invest in off-world infrastructure in exchange for future returns. This assumes enforceable contracts, predictable output, and stable governance. None of these conditions are guaranteed in isolated, high-risk environments. Investment remains speculative and limited. Debt-based systems also struggle. Debt relies on future surplus to repay present consumption. In environments without reliable growth, debt becomes unsustainable. Financial obligations accumulate without corresponding productive expansion. Defaults become systemic rather than exceptional. Technological depreciation accelerates economic decline. Equipment exposed to radiation, dust, and thermal extremes degrades faster than projected. Replacement cycles shorten. Capital stock erodes. Productivity falls even as maintenance effort increases. Human capital faces similar depreciation. Skills tied to complex systems degrade when systems simplify. Specialists lose practice opportunities. Knowledge becomes fragmented. Rebuilding expertise requires time and resources that are unavailable. Attempts to import Earth-style economic complexity into constrained environments misunderstand path dependence. Earth's economy evolved alongside its environment. It did not emerge in isolation. Transplanting economic structures without their environmental foundations produces instability rather than growth. Over time, the economy converges toward a narrow operating envelope. Activities outside survival maintenance become rare. Cultural production, scientific exploration, and creative industries decline. The settlement persists physically, but contracts economically and socially. This contraction reinforces dependence. As economic capacity shrinks, reliance on Earth increases. The settlement becomes less autonomous with time, not more. The original premise of independence erodes under the weight of constraint. The vision of a thriving off-world economy misunderstands what economies actually are. They are not engines that can run anywhere with sufficient management. They are emergent systems that require conditions no other planet currently provides. As economic systems contract, pressure shifts toward governance structures, which must manage scarcity directly. That transition introduces the next failure mode, where political systems inherit economic impossibilities they cannot resolve. Governance fails when survival becomes policy. Governance is often described as a matter of design. Constitutions, legal frameworks, and institutional structures are expected to provide stability regardless of environment. History shows otherwise. Governance systems are shaped less by ideals, and more by material conditions. When those conditions become permanently constrained, governance does not remain neutral. It changes form, priorities, and limits in ways that undermine long-term stability. On Earth, governance operates within abundance relative to survival needs. Even during crises, basic life support remains largely external to political control. Air, gravity, and ecosystems are not governed. They simply exist. This separation allows political systems to focus on coordination, justice, and long-term planning. Off-world settlements collapse this separation entirely. In isolated habitats, survival infrastructure becomes political infrastructure. Life support, energy allocation, food distribution, and medical access are inseparable from governance decisions. Every policy choice directly affects survival probability. This transforms governance from a mediating function into an operational one. Operational governance favors efficiency over legitimacy. Decisions must be made quickly. Consensus becomes costly. Debate is reframed as delay. Over time, authority concentrates not because leaders seek power, but because survival pressures reward decisiveness. Checks and balances weaken under the justification of necessity. This shift alters accountability. When failures occur, leaders can plausibly argue that no better alternatives existed. Outcomes are attributed to environment rather than decision-making. Transparency declines because exposing uncertainty undermines confidence. Governance becomes protective of its own authority. Legal systems degrade under constraint. Laws require enforcement, interpretation, and adjudication. Small populations lack institutional depth. Officials hold multiple roles. Conflicts of interest become unavoidable. Legal consistency erodes as exceptions proliferate. Rule-based governance gives way to case-by-case discretion. Democratic mechanisms struggle under these conditions. Elections require choice. Choice requires alternatives. In constrained environments, alternatives narrow. Candidates converge on survival priorities. Policy differences shrink. Participation becomes symbolic. Over time, engagement declines as outcomes appear predetermined. Authoritarian tendencies are not imposed from above. They emerge organically from operational necessity. When systems are fragile, deviation is perceived as risk. Conformity is rewarded. Dissent is framed as threat. Even well-intentioned governance slides toward control. Succession becomes a critical vulnerability. Leadership transitions introduce uncertainty. In small populations, talent pools are limited. Removing an experienced leader creates operational gaps. As a result, governance structures resist change. Tenure extends. Power ossifies. External oversight is minimal. Earth-based institutions cannot intervene effectively due to distance and delay. This isolation removes an important corrective force. Governance failures persist longer. Learning cycles slow. Mistakes repeat. Emergency powers become permanent. What begins as temporary authority during crises solidifies into standard practice. The definition of emergency expands subtly. Scarcity ensures that some form of crisis is always present. Exceptional governance becomes normal governance. Social trust erodes under these dynamics. When governance controls survival resources, perceptions of fairness matter intensely. Any perceived bias triggers resentment. Yet perfect fairness is impossible under scarcity. Attempts to correct inequity create new grievances. Cultural stagnation compounds governance fragility. Shared narratives justify authority. In isolated environments, narratives narrow. History compresses. Myth replaces memory. Governance legitimacy relies increasingly on necessity rather than consent. Generational turnover intensifies conflict. Those born into constrained systems did not choose them. Governance structures designed by founders reflect assumptions that no longer hold. Younger generations question legitimacy without seeing viable alternatives. Tension rises without resolution. Conflict resolution mechanisms weaken. On Earth, dissatisfied groups can relocate, secede, or reform institutions. Off-world, exit options do not exist. Conflict becomes internalized. Suppression replaces resolution. Militarization of governance emerges subtly. Security responsibilities expand to include infrastructure protection and behavioral enforcement. Surveillance increases. Privacy contracts. These measures are justified as protective, but they alter social dynamics permanently. The idea that better governance models can solve these problems misunderstands the driver. Governance failure is not primarily ideological, it is environmental. When survival is policy, politics loses flexibility. This does not mean governance collapses immediately. It adapts. It becomes functional in the short term and brittle in the long term. Stability is maintained by suppressing variability rather than accommodating it. Over decades, governance systems lose the capacity to reform themselves. Every reform introduces risk. Risk is avoided. Stagnation follows. Governance survives, but it does not evolve. Earth-based governance survives because environmental stability allows institutional experimentation. Failed policies do not usually threaten immediate survival. Off-world governance lacks this margin. The promise of exporting political systems into space assumes that governance is portable. It is not. It is anchored to conditions that do not exist beyond Earth. As governance becomes rigid, economic contraction accelerates. As economic contraction accelerates, governance assumes greater control. The feedback loop tightens. Political systems inherit problems they cannot solve. This is not a failure of leadership or ideology. It is the predictable outcome of governing under permanent constraint. Governance adapts to environment. In hostile environments, it adapts in ways that trade long-term resilience for short-term control. This convergence reveals a deeper pattern. Every system that supports civilization depends on conditions Earth uniquely provides. When those conditions vanish, systems do not scale outward, they fold inward. The next constraint follows inevitably. When governance hardens and economies stagnate, innovation slows, and without sustained innovation, survival itself becomes temporary rather than permanent. Innovation collapses without breathing room. Innovation is often described as humanity's ultimate safeguard. When environments are harsh, the assumption is that innovation will compensate. New tools, new methods, and new technologies are expected to overcome physical and social limitations. This belief underpins much of the optimism surrounding off-world settlement. However, innovation does not emerge simply because it is needed. It requires specific conditions that do not exist in permanently constrained environments. On Earth, innovation thrives because failure is usually survivable. Most experiments do not succeed, and most new ideas do not work as intended. The cost of failure is absorbed by redundancy, scale, and diversity. A failed prototype does not threaten the stability of civilization. A failed policy does not usually compromise basic life support. This tolerance for failure is the substrate on which innovation grows. Off-world environments reverse this dynamic. Failure is not an inconvenience, it is a direct threat. When life support systems are tightly coupled and margins are thin, experimentation becomes dangerous. The safest choice is to preserve what already works, even if it is inefficient or outdated. Over time, this conservatism becomes institutionalized. Innovation also depends on surplus resources. Research and development consume time, energy, materials, and labor that do not yield immediate returns. On Earth, surplus allows societies to allocate resources toward long-term gains. Off-world settlements operate under constant scarcity. Every unit of energy diverted to experimentation is energy not used for survival maintenance. Every hour spent developing something new is an hour not spent keeping existing systems operational. Population size further constrains innovation. Breakthroughs rarely come from isolated individuals. They emerge from networks of collaboration, competition, critique, and refinement. Large populations support specialization and intellectual diversity. Small populations converge toward homogeneity. Ideas circulate within narrow channels. Novel perspectives become rare. Educational systems reflect this constraint. Training focuses on operational competence rather than exploratory thinking. Skills are taught to maintain systems, not to reimagine them. Over generations, intellectual breadth contracts. Innovation becomes incremental rather than transformative. Isolation accelerates this contraction. Earth-based innovators draw on global knowledge pools. They attend conferences, collaborate across institutions, and build on parallel work. Off-world innovators operate with delayed communication and limited bandwidth. Collaboration slows. Verification takes longer. Errors persist. Risk aversion compounds these effects. When failure carries existential consequences, organizations reward caution. Incentives favor reliability over creativity. Individuals who propose disruptive ideas are perceived as destabilizing rather than visionary. Innovation becomes a liability rather than an asset. Technological stagnation emerges gradually. Early settlers bring advanced tools and knowledge. Over time, equipment degrades. Replacement parts become scarce. Local manufacturing struggles to maintain precision. Without continuous infusion of innovation, technology plateaus and then declines. This decline is not always obvious. Systems continue to function, but with increasing effort. Maintenance schedules tighten. Repairs become improvised. Performance drifts. The system appears stable until cumulative degradation crosses a threshold. Automation does not resolve this problem. Automated systems require continual updating and oversight. They embed assumptions about operating conditions that may no longer hold. When automated systems fail, human operators must intervene. If innovation has stagnated, those interventions become less effective. The myth of innovation as an automatic response to adversity ignores historical precedent. Societies under constant survival pressure do not innovate faster, they innovate less. Historical examples show that periods of extreme constraint correlate with technological stagnation, not acceleration. Wartime innovation is often cited as a counterexample. However, wartime societies still operate within Earth's abundance. They redirect resources temporarily, but retain industrial depth and external support. Off-world settlements lack that depth. Long-term innovation requires not only freedom to fail, but freedom to rethink goals. In constrained environments, goals are fixed, survival dominates. Questioning foundational assumptions becomes risky. Innovation narrows to optimization within existing frameworks rather than paradigm shifts. Cultural factors reinforce this narrowing. Narratives emphasize endurance and resilience rather than exploration. Foundational myths celebrate stability. Over time, creativity is reframed as irresponsibility. This cultural shift reduces innovation capacity independent of technical skill. Generational effects are critical. Children raised in constrained environments internalize caution. Their aspirations align with system preservation rather than transformation. Even if external knowledge remains accessible, internal motivation shifts. Earth's innovation engine is powered by excess. Excess energy, excess food, excess labor, and excess time allow humans to experiment. Off-world environments are defined by the absence of excess. This absence cannot be engineered away. As innovation slows, adaptation capacity shrinks. Systems become brittle. Unexpected challenges cannot be met with novel solutions. Instead, existing tools are stretched beyond design limits. Failure probability increases. This creates a feedback loop. Reduced innovation increases risk. Increased risk reinforces conservatism. Conservatism further reduces innovation. The system stabilizes briefly at a lower capability level, then degrades again. The belief that artificial intelligence or advanced computation will bypass this dynamic misunderstands their dependency on human context. These tools amplify existing capacity. They do not generate surplus or tolerance for failure. Without an environment that supports exploration, their impact remains limited. Innovation also depends on meaning beyond survival. Humans innovate not only to endure, but to improve quality of life, expand understanding, and pursue curiosity. When existence narrows to maintenance, motivation erodes. Creativity suffers. This is not a temporary phase. Permanent constraint produces permanent suppression of innovation. Over decades, the gap between Earth-based and off-world capability widens. Earth continues to evolve. Off-world settlements fall behind. At that point, dependence deepens rather than recedes. Off-world populations rely increasingly on Earth for technological renewal. Independence becomes less attainable over time, not more. The original promise of becoming multiplanetary assumed that humanity could transplant its innovative capacity into new environments. This assumption fails because innovation is not portable, it is emergent. It arises from conditions that Earth uniquely provides. Without sustained innovation, survival becomes a countdown rather than an open-ended project. Systems age. Knowledge ossifies. The settlement persists until a failure occurs that cannot be solved with existing tools. This realization reframes the entire multiplanetary narrative. Expansion does not create new engines of progress. It creates outposts dependent on a single irreplaceable source of renewal. That source is Earth. The next constraint follows directly. When innovation stalls and governance hardens, the ability to recover from major shocks disappears. And without recovery, permanence is an illusion rather than a goal. Biological fragility in alien environments. Humanity often frames the challenge of becoming multiplanetary as an engineering problem. We talk about rockets, habitats, propulsion, energy systems, and terraforming, as if survival beyond Earth is simply a matter of sufficient technology and time. But beneath every plan to settle Mars or build permanent colonies elsewhere lies a constraint that technology cannot redesign at will: the human body itself. Our biology is not adaptable in the way science fiction often implies. It is narrow, fragile, and deeply optimized for a single planetary environment. This biological rigidity is not a temporary obstacle. It is the central reason long-term, self-sustaining human expansion beyond Earth remains fundamentally unrealistic. Human physiology evolved under extremely specific conditions. Earth provides a precise gravity level, a protective magnetic field, a dense atmosphere, stable pressure, a narrow temperature range, and a chemical environment tuned to our cellular processes. Remove or alter even one of these variables, and the body begins to degrade. Spaceflight research has already shown this clearly. Astronauts experience muscle atrophy, bone density loss, vision impairment, immune dysfunction, cardiovascular changes, and neurological effects after relatively short missions. These effects are not cosmetic or minor. They represent systemic breakdowns caused by environments our bodies were never designed to tolerate. Microgravity is one of the most studied threats. In orbit, bones lose calcium at rates comparable to severe osteoporosis. Muscles weaken despite constant exercise. The heart changes shape and function because it no longer works against gravity. Even with advanced countermeasures, these effects accumulate. On Mars, gravity is only about 38% of Earth's. On the Moon, it is roughly 16%. There is no evidence that humans can live for generations under these conditions without severe and possibly irreversible consequences. Artificial gravity habitats are often proposed as a solution, but maintaining large, rotating structures indefinitely introduces massive engineering, energy, and stability challenges that scale poorly over time. Radiation exposure presents an even more serious biological barrier. Earth's magnetic field and thick atmosphere shield us from most cosmic and solar radiation. Outside this protection, radiation damages DNA, increases cancer risk, disrupts reproduction, and accelerates aging. Mars has a weak magnetic field and a thin atmosphere. Measurements from robotic missions show radiation levels far above what is considered safe for humans over a lifetime. Shielding habitats can reduce exposure but not eliminate it. More importantly, shielding entire planetary environments or enabling safe outdoor activity is not realistically achievable with foreseeable technology. Reproduction is another unresolved problem. No mammal has ever been conceived, gestated, born and raised entirely in low-gravity or high-radiation environments. We do not know how embryonic development responds to altered gravity fields. We do know that radiation damages reproductive cells and increases the likelihood of genetic abnormalities. A multiplanetary species requires stable, healthy reproduction across generations. Without that, settlements remain temporary outposts, dependent on Earth, not independent civilizations. Psychological and neurological health further complicate the picture. Humans evolved in complex social environments with natural sensory inputs, open skies, changing landscapes, biological rhythms, and rich ecosystems. Long-term isolation in confined artificial habitats leads to cognitive decline, mood disorders, impaired decision-making, and social instability. These are not hypothetical concerns. They are documented in submarines, polar research stations, and long-duration space missions. Scaling these conditions to entire societies multiplies the risk. A colony that cannot maintain psychological health cannot maintain political stability, cooperation, or continuity. Adaptation through genetic modification is sometimes suggested as a way forward. In theory, humans could be altered to tolerate radiation, low gravity, or different atmospheric compositions. In practice, this introduces ethical, technical, and evolutionary problems of enormous magnitude. Modifying complex traits involves unpredictable trade-offs. Changes that improve survival in one environment may cause failures in others. Over time, genetically diverged populations would no longer be biologically compatible, undermining the idea of a unified human species. More importantly, such interventions would require levels of biological control and long-term planning that humanity has never demonstrated. Even if these biological challenges could be partially mitigated, they cannot be fully removed. Life support systems can fail. Shielding can degrade. Habitats can suffer accidents. On Earth, failure modes are buffered by a vast, self-repairing biosphere. Off Earth, every system is artificial, closed, and brittle. A single cascading failure can be fatal to an entire settlement. Biological fragility amplifies this risk because human bodies have little tolerance for environmental deviation. Survival margins remain thin, even with advanced technology. The idea of becoming multiplanetary often assumes that humans are flexible enough to occupy new worlds if we simply build the right machines. The evidence suggests the opposite. We are deeply earthbound organisms. Our biology is not a general-purpose system capable of thriving anywhere. It is a specialized product of one planet, shaped by billions of years of evolution under stable conditions that do not exist elsewhere in our solar system. Technology can extend our reach temporarily, but it cannot rewrite the fundamental constraints of our biology. Long-term evolutionary adaptation also fails as a realistic solution when examined closely. Evolution operates over immense timescales and requires stable populations exposed to consistent selective pressures. Off-world settlements would be small, vulnerable, and dependent on technological life support. Any environmental change, equipment failure, or supply interruption would likely kill individuals faster than evolutionary processes could respond. Natural selection cannot compensate for lethal radiation exposure or zero-gravity bone loss when the organism dies before reproducing successfully. Evolution is not a design tool that can be accelerated safely to meet engineering timelines. Nutrition and microbiology add further layers of difficulty. Human digestion relies on complex interactions between diet, gut bacteria, and immune function. Spaceflight has already shown that microgravity alters the human microbiome in unpredictable ways, weakening immunity and increasing inflammation. Growing food in closed systems introduces nutritional deficiencies, contamination risks, and reduced dietary diversity. Earth's ecosystems constantly recycle nutrients through vast biological networks. Artificial systems must replicate this perfectly, indefinitely, without collapse. Any long-term imbalance affects human health directly, often subtly at first, then catastrophically. Immune system degradation is another underappreciated constraint. Studies show that spaceflight suppresses immune responses and reactivates dormant viruses. The immune system evolved under constant exposure to Earth-based pathogens and environmental signals. Remove those signals and immune regulation falters. In a closed habitat, a single mutated pathogen or microbial imbalance could spread rapidly through a population with weakened defenses. On Earth, disease outbreaks are mitigated by scale, mobility, and environmental diversity. In space habitats, they become existential threats. Even basic wound healing behaves differently outside Earth conditions. Bone fractures heal more slowly in low gravity. Muscle repair is impaired. Blood flow dynamics change. Medical emergencies that are routine on Earth become life-threatening when evacuation is impossible and supplies are limited. Advanced medicine depends on infrastructure, specialists, and supply chains that are difficult to reproduce beyond Earth at scale. A multiplanetary civilization would require fully autonomous medical ecosystems capable of handling every possible contingency without external support. No such system exists. Time itself becomes a biological stressor. Circadian rhythms depend on consistent day-night cycles. Mars has a similar but not identical day length. Other environments differ dramatically. Disrupted circadian rhythms affect sleep, hormone regulation, mental health, and long-term disease risk. Artificial lighting can approximate cycles, but subtle mismatches accumulate. Over generations, chronic circadian disruption could alter development, cognition, and population health in ways that are difficult to predict or reverse. Taken together, these constraints point to a sobering conclusion. Human survival beyond Earth is not limited by imagination, but by biological reality. We can visit other worlds, study them, and even live there briefly. But permanence requires compatibility at a cellular, genetic, and systemic level that does not exist. The more we understand human biology, the clearer this incompatibility becomes. Becoming multiplanetary would require not just building habitats, but creating entirely new biological contexts in which humans can function without constant decline. That challenge is orders of magnitude harder than launching rockets or constructing bases. It is not a problem of insufficient effort. It is a mismatch between a species and environments fundamentally hostile to its design. Until biology itself changes, not through speculation but through proven, stable, multi-generational evidence, humanity remains bound to Earth. Other worlds may host our machines, our instruments, and our temporary presence. But the human body, in its current form, has only one true home. This reality does not diminish exploration or curiosity, but it demands honesty about limits, risks, and trade-offs, reminding us that protecting Earth may ultimately be the most practical strategy for preserving human civilization across deep time and ensuring continuity of life as we understand it. Energy limits that cannot be escaped. The idea of humanity becoming a multiplanetary species often assumes that energy is a solvable problem. Rockets will get cheaper, reactors will become more efficient, and solar power will scale outward from Earth. In this vision, energy is treated as an engineering hurdle rather than a fundamental constraint. But when examined closely, energy availability is not just a challenge. It is a hard limit that defines what kinds of civilizations are physically possible. And it places severe restrictions on long-term human expansion beyond Earth. Every stable civilization is ultimately an energy system. Food production, manufacturing, transportation, healthcare, communication, and defense all depend on continuous energy input. On Earth, this energy comes from a rare combination of sources: abundant sunlight, fossil fuels accumulated over hundreds of millions of years, a thick atmosphere that supports weather systems, and a biosphere that recycles materials at planetary scale. No other known body in the solar system offers this combination. Removing Earth from the equation does not reduce energy demands, it increases them dramatically. Launching material off Earth already consumes enormous energy. Maintaining human life off Earth multiplies that cost. Every kilogram of water, air, food, equipment, and shielding must be transported, manufactured locally, or recycled with near-perfect efficiency. Each of these processes requires energy, not once, but continuously. A failure in energy supply does not merely reduce quality of life, it ends the settlement entirely. Mars is often presented as the most realistic candidate for long-term colonization, yet its energy environment is deeply hostile. Solar energy on Mars is weaker than on Earth due to distance from the Sun and frequent dust storms that can cover the entire planet for months. Nuclear reactors can provide steady power, but they introduce long-term risks, require complex maintenance, and depend on supply chains that do not yet exist beyond Earth. More importantly, nuclear energy does not scale easily. A growing population requires exponentially more infrastructure, security, waste management, and redundancy. Energy storage is another critical bottleneck. On Earth, energy systems rely on massive grids, diverse generation sources, and geographic distribution. Off Earth, energy systems are isolated and fragile. Batteries degrade, reactors age, solar panels accumulate damage from radiation and micrometeoroids. There is no external grid to compensate for local failure. Every settlement must be energy self-sufficient at all times, without exception. That requirement alone places an upper limit on population size and complexity. The problem becomes even more severe when considering industrial activity. A self-sustaining civilization cannot rely on imported machinery forever. It must mine raw materials, refine metals, manufacture electronics, and repair advanced systems locally. These processes are among the most energy-intensive activities humans perform. Earth supports them because it has thick crusts rich in accessible minerals, liquid water for cooling and processing, and gravity that enables efficient separation and manufacturing techniques. Other planets lack many of these advantages. Asteroid mining is often proposed as a solution, but it introduces its own energy paradox. Reaching asteroids, extracting materials, processing them, and transporting them to habitats requires more energy than it saves, at least with current or near-future technology. The energy return on investment remains low, especially when factoring in losses, failures, and maintenance. Without a massive surplus of cheap energy, industrial ecosystems cannot form. Energy constraints also shape political and social stability. On Earth, energy shortages cause unrest, economic collapse, and conflict even when alternatives exist. In off-world settlements, shortages would be immediate and lethal. Energy rationing would not be a policy debate, it would be a survival decision. Such conditions create rigid hierarchies, extreme control over resources, and constant risk of systemic collapse. A society that exists one power failure away from extinction is not resilient. It is brittle. Heat management presents another overlooked challenge. Energy use produces waste heat. On Earth, this heat dissipates through atmosphere and oceans. In space or thin atmosphere environments, heat must be actively removed. Radiators require surface area, structural mass, and precise orientation. As energy consumption increases, so does waste heat, placing an upper limit on how much power a settlement can safely use. This is not a technical inconvenience. It is a thermodynamic constraint. Even hypothetical advanced energy sources do not eliminate the problem. Fusion power, if achieved, would still require complex containment, rare materials, and constant maintenance. It would still generate heat, radiation, and waste. More importantly, it would still need to be built, fueled, repaired, and expanded within an environment that actively degrades infrastructure. A fusion reactor on Mars does not operate under the same conditions as one on Earth. Dust infiltration, temperature extremes, and radiation increase failure rates and maintenance demands. Long-term energy planning also faces a timescale problem. Civilizations are not measured in years or decades, but centuries and millennia. Energy systems must operate continuously across generations without catastrophic interruption. On Earth, civilizations collapse, but humanity survives because energy flows continue through ecosystems and natural cycles. Off Earth, there is no fallback. Once an energy system fails, recovery may be impossible. The farther a settlement is from Earth, the worse this problem becomes. Communication delays prevent real-time support. Resupply missions become rare or infeasible. Energy infrastructure must be overbuilt to account for unknown risks, further increasing material and energy costs. At some point, the energy required to sustain the settlement exceeds what the environment can reliably provide. This reality undermines the idea of exponential expansion across multiple planets. Each new settlement does not reduce risk, it multiplies it. Each one requires independent energy ecosystems capable of handling worst-case scenarios indefinitely. History shows that humans struggle to maintain even Earth-based infrastructure over long periods without degradation. Expecting flawless performance in hostile extraterrestrial environments contradicts everything we know about complex systems. Energy abundance is what allowed modern civilization to emerge on Earth. Fossil fuels provided a temporary energy surplus that accelerated growth, innovation, and population expansion. That surplus is unique. It does not exist elsewhere in the solar system. Renewable sources off Earth are weaker and less reliable. Nuclear sources are limited and dangerous at scale. There is no hidden energy reserve waiting to be tapped. In this context, becoming multiplanetary is not a question of ambition, funding, or courage. It is a question of physical limits. Energy determines what can be built, sustained, and defended. Without a stable, scalable, and resilient energy foundation, permanent human civilization cannot take root beyond Earth. This does not mean exploration should stop. Robotic missions, scientific outposts, and temporary human presence all remain valuable. But permanence demands energy conditions that no other known world provides. Ignoring this reality leads to plans that collapse under scrutiny. Earth remains exceptional not because it is convenient, but because it is energetically rich in ways that are extremely rare. Until an environment offers comparable energy flows, any attempt at true multiplanetary civilization will remain dependent, fragile, and ultimately unsustainable. Energy is not just one challenge among many. It is the boundary that defines the possible. And at present, that boundary keeps humanity firmly anchored to one planet. The biological limits. Humans cannot engineer away. Human expansion beyond Earth is often framed as a technological challenge, but the most severe constraints are biological. Human bodies evolved under very specific planetary conditions that cannot be replicated easily, reliably, or permanently elsewhere. These limits are not superficial discomforts. They are structural vulnerabilities that emerge over time and intensify with duration, making permanent off-world civilization fundamentally unstable. Gravity is the first and most immediate issue. Earth's gravity shaped human anatomy at every level, from bone density and muscle mass to cardiovascular function and inner ear balance. In microgravity or partial gravity environments, these systems degrade rapidly. Astronauts experience bone loss at rates of up to 1% per month despite rigorous exercise. Muscles atrophy, the heart weakens, vision changes due to fluid redistribution in the skull. These effects are not temporary inconveniences. Many persist long after return to Earth, and some may be irreversible. Mars, often proposed as a second home, offers only 38% of Earth's gravity. No long-term studies exist on human development under such conditions because none are possible yet. However, existing data strongly suggests that human bodies cannot maintain Earth-like health in reduced gravity indefinitely. Children born in such environments would likely develop entirely different physiological baselines, making return to Earth impossible and creating a population biologically incompatible with its origin world. Radiation presents an even more serious threat. Earth is protected by a strong magnetic field and thick atmosphere that block most cosmic and solar radiation. Outside this shield, exposure increases dramatically. Long-duration astronauts already show elevated cancer risk, DNA damage, and neurological effects. On Mars, or in deep space habitats, radiation exposure would be continuous and unavoidable. Shielding can reduce exposure but not eliminate it. Effective radiation shielding requires large amounts of mass, which increases launch costs and structural complexity. Even with heavy shielding, secondary radiation created by particle collisions can penetrate habitats. Over decades, accumulated damage would raise cancer rates, impair fertility, and increase cognitive decline. These are not speculative risks. They are documented biological responses to known radiation levels. Reproduction introduces another layer of uncertainty. No human has ever conceived, gestated, or given birth in space or reduced gravity. Animal studies suggest significant risks, including abnormal development, compromised immune systems, and impaired organ formation. Radiation exposure during early development increases the likelihood of severe defects. Even if conception were possible, the probability of producing healthy offspring consistently is unknown and likely low. The immune system also behaves differently off Earth. Microgravity alters immune response, reducing effectiveness and increasing vulnerability to infection. Latent viruses have been shown to reactivate in astronauts under spaceflight conditions. Stress, radiation, and isolation compound these effects. In a closed habitat, where microbial ecosystems evolve alongside humans, even minor infections could become lethal. Psychological limits further constrain long-term settlement. Human cognition evolved in open environments with natural light cycles, diverse sensory input, and social flexibility. Space habitats and planetary bases are confined, artificial, and monotonous. Long-duration missions already show increased rates of depression, anxiety, sleep disorders, and interpersonal conflict. These effects intensify with isolation and cannot be fully mitigated through training or technology. Social dynamics under permanent confinement pose additional risks. Small populations are vulnerable to conflict, power imbalances, and cultural stagnation. There is no escape valve for dissent, no geographic separation to diffuse tension, and no external environment to absorb failure. Over generations, such conditions are likely to produce rigid hierarchies or collapse entirely. Medical care presents another unsolved problem. Advanced healthcare relies on large populations, specialized expertise, and complex supply chains. Off-Earth, medical facilities would be limited, equipment would degrade, and replacement parts would be scarce. Surgical complications, chronic illness, or rare conditions could become fatal simply due to lack of resources. Aging compounds all of these issues. Bone loss, radiation exposure, immune suppression, and psychological stress all worsen with age. A population that cannot age healthily cannot sustain institutional memory, technical knowledge, or leadership continuity. Over time, this erodes the functional capacity of the settlement. Adaptation through genetic modification is often suggested as a solution, but it introduces ethical, technical, and social challenges that exceed current understanding. Modifying humans to survive off Earth would create populations fundamentally different from those on Earth. This raises questions about identity, rights, and long-term viability. It also assumes precise control over complex biological systems that science does not yet possess. Even if such modifications were possible, they would not eliminate environmental dependence. Modified humans would still require controlled atmospheres, stable temperatures, radiation shielding, and reliable nutrition. Biology cannot be separated from environment. It can only be tuned within narrow margins. Evolution itself operates too slowly to solve these problems. Natural selection requires large populations and long timescales. Off-world settlements would have neither. Instead of adaptation, genetic drift and accumulated damage would dominate, increasing the likelihood of decline rather than improvement. The idea that humans can simply engineer their way past biological limits misunderstands the nature of those limits. Technology can assist biology, but it cannot rewrite the fundamental conditions under which complex organisms function. Life is not modular. It is deeply integrated with its environment. Earth supports human biology through countless subtle mechanisms: atmospheric pressure that enables efficient oxygen exchange, gravity that maintains skeletal integrity, magnetic shielding that protects DNA, and ecosystems that regulate disease and nutrition. Replicating all of this artificially, indefinitely, and without failure is beyond any credible engineering roadmap. Short-term survival off Earth is possible, long-term habitation is plausible, but permanent independent civilization requires biological stability across generations. That stability depends on conditions humans did not evolve to tolerate elsewhere. This does not mean humans will never leave Earth. It means they will remain biologically tethered to it. The farther they go, the more artificial support is required, and the more fragile the system becomes. In the end, biology imposes constraints that technology cannot fully overcome. Human bodies are not designed for space. They are products of Earth. Until that changes, becoming truly multi-planetary remains not just difficult, but biologically unsustainable. Energy dependence creates a permanent point of failure. Every proposal for a multi-planetary human future assumes that energy availability can be solved through engineering alone. In reality, energy dependence is not merely a technical challenge. It is a systemic vulnerability that compounds over time and introduces a single point of failure into every off-world settlement. Without continuous, abundant, and redundant energy input, no human habitat beyond Earth can function, let alone sustain a growing population. On Earth, energy systems exist within a forgiving environment. Power generation can fail temporarily, without immediate loss of life. Grids can be repaired using local materials, large workforces, and multiple overlapping technologies. Natural processes provide baseline support through gravity, atmosphere, and climate regulation. Off-Earth, energy systems are not supplemental. They are existential. Every critical life support function depends directly on energy. Oxygen generation, carbon dioxide removal, pressure maintenance, temperature control, water recycling, waste processing, food production, communication, medical equipment, and radiation shielding all require uninterrupted power. A brief outage on Earth is inconvenient. A brief outage off Earth is fatal. Redundancy is often cited as a safeguard, but redundancy increases complexity, mass, and maintenance burden. Each additional backup system introduces more components that can fail. Over time, redundancy itself becomes a liability as parts degrade and replacement becomes difficult. True redundancy requires independent systems with separate failure modes, which dramatically increases resource demands. Solar power, the most commonly proposed energy source, is unreliable outside Earth's orbit. On Mars, sunlight is weaker and frequently blocked by global dust storms that can last for months. During such events, solar output can drop to near zero. Energy storage systems would need to sustain entire settlements through prolonged darkness, an engineering challenge that scales poorly with population size. Nuclear power appears more reliable, but it introduces its own constraints. Reactors require specialized materials, precise control systems, and long-term waste management. Maintenance cannot be improvised. Reactor failure or contamination would be catastrophic in a closed environment. Transporting replacement fuel or components across interplanetary distances is neither rapid nor guaranteed. Small modular reactors reduce some risks, but not dependency. They still rely on complex cooling systems, trained personnel, and stable operating conditions. Human error, mechanical fatigue, or unforeseen interactions can cascade into system failure. On Earth, such failures are localized. Off Earth, they threaten the entire settlement simultaneously. Energy production also generates heat, which must be dissipated. In space, heat removal is inefficient because it relies on radiation rather than convection. As power usage increases, waste heat becomes harder to manage. Overheating can damage electronics, weaken structural materials, and compromise life support systems. Energy storage is another limiting factor. Batteries degrade over time and are sensitive to temperature extremes and radiation. Chemical storage systems require resupply. Mechanical storage adds mass and complexity. No storage solution currently exists that can reliably support large populations through extended generation outages without unacceptable risk. Energy infrastructure must also be protected from environmental hazards. Micrometeoroids, radiation, dust abrasion, thermal cycling, and material fatigue all accelerate degradation. Repairs require energy themselves, creating feedback loops where declining efficiency increases strain on remaining systems. Human factors exacerbate these risks. Energy systems require constant monitoring, calibration, and maintenance. In isolated environments, operator fatigue, stress, and skill degradation increase the likelihood of mistakes. Automation can reduce workload, but introduces dependence on software reliability and cybersecurity, both of which are vulnerable in isolated networks. Scaling energy systems is especially problematic. Doubling population does not simply double energy demand. It increases demand non-linearly due to expanded infrastructure, redundancy requirements, and thermal management. Each incremental expansion reduces overall system resilience unless energy capacity grows faster than population, which is rarely feasible. Energy scarcity shapes social structures. When power is limited, allocation becomes political. Decisions about who receives power during shortages determine survival. This concentrates authority and creates conflict. Over time, energy rationing becomes normalized, reducing quality of life and productivity. Economic activity cannot compensate for energy limits. Manufacturing, data processing, and transportation all depend on power availability. Without surplus energy, economic diversification collapses. Settlements become energy sinks rather than productive systems. Energy dependence also prevents true independence. As long as off-world settlements require specialized fuel, replacement parts, or expertise from Earth, they remain extensions rather than autonomous civilizations. Any disruption in supply chains threatens collapse. Long-term projections worsen the picture. Infrastructure ages, efficiency declines, maintenance demands increase. Energy output must rise just to maintain baseline function. Eventually, a point is reached where energy generation can no longer keep pace with system decay. Catastrophic failure does not require total loss of power. Partial failures can be just as deadly. Loss of pressure control, oxygen generation, or thermal regulation for even minutes can cause irreversible harm. Unlike Earth, there is no margin for error. Historical analogues are instructive. Isolated human systems under extreme energy constraints, such as submarines or polar stations, rely on constant resupply and strict operational limits. They are not self-sustaining civilizations. Scaling them up does not remove the constraint. It magnifies it. The belief that future technology will eliminate energy dependence ignores physical limits. Energy must come from somewhere. It must be generated, transmitted, stored, and dissipated. Each step introduces loss. Physics does not allow perfect efficiency. Even hypothetical breakthroughs such as fusion do not eliminate dependency. They reduce some risks while introducing others. Complex systems remain complex, and complexity remains fragile. A multiplanetary civilization requires energy systems that can fail gracefully, recover autonomously, and operate indefinitely without external support. No such system exists today, and no credible roadmap demonstrates how one could. Energy dependence therefore acts as a permanent ceiling on off-world human expansion. It enforces fragility, centralization, and vulnerability at every scale. As long as survival itself depends on uninterrupted power, human civilization cannot escape its planetary cradle. This constraint does not disappear with optimism or ambition. It is built into the physics of living off Earth. Until energy becomes abundant, fail-safe, and locally renewable at scale, becoming truly multiplanetary remains an aspiration constrained by reality. Time delays prevent civilizational coherence. The final assumption behind a multiplanetary future is that distance can be managed through communication. This belief underestimates the structural importance of time in human civilization. Communication delay is not an inconvenience that technology smooths over. It is a fundamental barrier that reshapes governance, coordination, economics, and social identity. Once distances impose unavoidable time lags, a civilization stops functioning as a unified system. On Earth, human systems evolved under near-instant communication. Even before modern technology, delays were measured in days or weeks, not minutes or hours. Today, coordination occurs in real time. Markets respond instantly. Emergencies are addressed immediately. Cultural norms propagate rapidly. These properties are not cosmetic. They are foundational to modern civilization. Off Earth, time delays grow unavoidable. A signal between Earth and Mars can take anywhere from 4 to 24 minutes one way depending on orbital positions. That delay doubles for responses. For more distant settlements, delays extend into hours. These delays cannot be engineered away. They are imposed by the finite speed of light. Real-time decision-making becomes impossible under these conditions. Instructions arrive too late to address fast-moving problems. Autonomous authority must replace centralized control. This fragmentation alters governance fundamentally. Local decision-makers gain absolute power by necessity, not design. Oversight becomes retrospective rather than preventative. Emergency response illustrates the problem clearly. On Earth, crises trigger immediate coordination across institutions. Off Earth, emergencies must be handled entirely locally. External expertise cannot intervene in time. Mistakes cannot be corrected remotely. Accountability arrives after outcomes are fixed. Economic coordination degrades similarly. Markets rely on synchronized information. Prices reflect current conditions. Delays distort signals. Arbitrage becomes impossible. Supply chains lose efficiency. Planning horizons shrink. Local economies decouple from Earth-based ones, not through independence, but through isolation. Scientific collaboration suffers as well. Modern research depends on rapid feedback, peer review, and data sharing. Delayed communication slows iteration. Errors persist longer. Breakthroughs take more time. Isolated research communities drift from global standards and lose relevance. Cultural divergence accelerates under delay. Shared narratives require shared timing. When information arrives late, context is lost. Events are interpreted differently. Humor, language, and norms drift. Over generations, identity fractures. Off-world populations no longer perceive themselves as part of the same society. Legal systems cannot function coherently across time gaps. Laws require enforcement and interpretation. Appeals require timely review. Precedents require consistent application. With delays, legal authority localizes. Earth-based law becomes symbolic rather than operational. Military and security coordination becomes untenable. Strategic decisions rely on timely intelligence. Delayed information produces miscalculation. Deterrence weakens. Defense becomes localized and reactive. Unified security doctrine collapses. Education systems fragment. Curricula diverge. Standards drift. Accreditation loses meaning. Knowledge evolves differently in isolated contexts. Over time, intellectual compatibility declines. Even basic social interaction is affected. Conversations lose immediacy. Emotional connection weakens. Empathy relies on shared experience in shared time. Delay erodes that synchrony. Relationships become abstract. Attempts to mitigate delay through predictive systems or artificial intelligence do not solve the core issue. Prediction introduces uncertainty. Autonomous systems amplify errors. Human trust erodes when decisions are made by distant algorithms without transparency. Historical analogs show similar patterns at smaller scales. Isolated communities diverge culturally and politically, even with modest separation. Communication delay accelerates that divergence dramatically. The assumption that digital communication preserves unity ignores the role of simultaneity. Seeing the same message is not the same as experiencing the same moment. Civilization depends on shared temporal reference points. Time delay also undermines legitimacy. Authority relies on responsiveness. When decisions arrive late, they lose relevance. Local actors ignore external input. Over time, external authority becomes ceremonial. This process is irreversible. Once systems adapt to delay, reintegration becomes difficult. Practices diverge. Trust erodes. Coordination costs rise. Eventually, separation becomes normalized. Multi-planetary civilization assumes cohesion across distance. Physics forbids it. What emerges instead are independent systems with shared ancestry but divergent trajectories. This does not require conflict. It occurs through structural drift. Over time, shared goals fragment into local priorities. Alignment weakens. The idea that humanity can spread across planets while remaining one civilization misunderstands how civilizations function. They are not defined by species alone, but by synchronized systems. Without shared time, synchronization fails. Without synchronization, civilization dissolves into separate entities. This does not mean off-world societies cannot exist. It means they cannot remain integrated into a single civilizational framework. Distance imposes delay. Delay imposes autonomy. Autonomy imposes divergence. The chain is unavoidable. In the end, time is the most restrictive boundary of all. It cannot be engineered away. It defines the scale at which human systems can operate coherently. As settlements move farther from Earth, coherence decays. What remains are disconnected societies linked by history, not function. This reality reframes the multi-planetary dream. Expansion does not create resilience through unity. It creates separation through physics. Civilization is not just about surviving in multiple locations. It is about remaining connected in meaningful ways. Time prevents that. Until faster-than-light communication exists, and there is no evidence it ever will, humanity cannot form a coherent civilization across planets. Distance turns time into a wall no spacecraft can cross. Ecological dependence cannot be recreated artificially. Human survival is not sustained by technology alone. It is sustained by a vast interconnected ecological system that operates continuously, invisibly, and without centralized control. Earth's biosphere is not a backdrop to civilization. It is an active life support engine refined over billions of years. Every attempt to become multiplanetary must confront the reality that this system cannot be replicated artificially at scale or over long periods. Earth's ecology performs countless functions simultaneously. It regulates atmospheric composition, stabilizes climate, cycles nutrients, manages waste, suppresses disease, and buffers environmental shocks. These processes are distributed across oceans, forests, soils, microorganisms, and atmospheric systems. No single component is responsible. The system works because of its complexity, redundancy, and constant feedback. Artificial environments attempt to simplify this complexity into controllable systems. Closed-loop life support, hydroponics, and bioreactors are often cited as substitutes. While these systems can sustain small populations temporarily, they lack the resilience and adaptability of natural ecosystems. They are brittle by comparison, vulnerable to cascading failure. Closed ecosystems require precise balance. Oxygen production must match consumption exactly. Carbon dioxide removal must remain continuous. Nutrient cycles must be tightly controlled. On Earth, fluctuations are absorbed by scale. In artificial systems, fluctuations accumulate. Small errors propagate. Over time, instability increases rather than dissipates. Food production illustrates this limitation clearly. Earth agriculture relies on soil microbiomes, pollinators, seasonal variation, and genetic diversity. Artificial agriculture depends on controlled inputs, limited crop varieties, and constant monitoring. Disease outbreaks spread faster in uniform systems. Crop failure has no backup when biodiversity is minimal. Microbial ecosystems pose another challenge. humans coexist with trillions of microorganisms that support digestion, immunity, and overall health. These microbial communities are shaped by environment, diet, and exposure. Artificial habitats alter these interactions in unpredictable ways. Studies aboard space stations show shifts in microbial populations, including increased virulence and antibiotic resistance. Waste recycling is similarly constrained. On Earth, waste is processed by vast networks of organisms over time. Artificial systems must process waste rapidly and completely. Any interruption leads to contamination. Chemical buildup becomes dangerous. System shutdown is not an option. Water cycling is deceptively complex. Earth's hydrological cycle purifies water through evaporation, precipitation, filtration, and biological activity. Artificial recycling systems rely on mechanical and chemical processes that degrade over time. Filters clog. Components wear out. Contaminants accumulate. Atmospheric stability is perhaps the most underestimated factor. Earth's atmosphere is maintained by interactions between life and geology. Oxygen levels, carbon dioxide concentrations, and trace gases are regulated dynamically. Artificial atmospheres require constant adjustment. Sensor errors or mechanical failures can be fatal within minutes. Ecosystems also provide psychological stability. Natural environments reduce stress, improve cognition, and support mental health. Artificial habitats cannot replicate these effects fully. Simulated nature does not engage human perception in the same way. Over time, psychological strain increases. Ecological resilience is built on diversity. Multiple species perform overlapping functions. If one fails, others compensate. Artificial systems are optimized for efficiency, not redundancy. Efficiency reduces tolerance for failure. Redundancy increases mass and complexity beyond practical limits. Scaling artificial ecosystems magnifies these issues. Supporting thousands or millions of people would require ecosystems of comparable complexity to Earth's, but without Earth's size, gravity, or geological support. No credible design demonstrates how such systems could remain stable for centuries. External environments offer no relief. Mars, the Moon, and other bodies lack native biospheres. There is no soil regeneration, no atmospheric buffering, no natural water cycling. Everything must be imported or manufactured. Any loss is permanent. Terraforming is often proposed as a long-term solution. However, altering a planet's atmosphere, temperature, and ecology to support Earth-like life would require immense energy and timescales measured in thousands or millions of years. Even then, the result would not replicate Earth's biosphere. Earth's ecology is the product of coevolution. Life shapes the planet, and the planet shapes life. Artificial systems lack this feedback loop. They are static by design, while life is dynamic by nature. This mismatch creates instability. Historical attempts at closed ecosystems provide sobering evidence. Experiments such as Biosphere 2 experienced oxygen depletion, species collapse, and psychological stress despite extensive planning and funding. These failures occurred on Earth, with external support available. Off-Earth, failure margins are thinner. There is no external ecosystem to compensate. No emergency influx of resources, no gradual recovery. Collapse is abrupt. Ecological dependence also limits population growth. Earth supports billions because its biosphere scales naturally. Artificial systems scale linearly at best, often exponentially in cost and complexity. Growth becomes a liability rather than an advantage. Long-term sustainability requires self-repair. Earth's ecosystems heal after disturbance through succession and adaptation. Artificial systems require intervention. Over time, intervention becomes harder as knowledge erodes and systems age. Climate regulation is inseparable from ecology. Earth's climate stability emerges from ocean currents, vegetation, and atmospheric chemistry. Artificial environments must regulate temperature actively, consuming energy continuously. Any interruption is immediately dangerous. Disease dynamics further complicate matters. high-density closed populations provide ideal conditions for pathogen evolution. Earth mitigates this through spatial separation and biodiversity. Artificial habitats amplify risk. Human culture evolved in ecological context. Rituals, seasons, food practices, and social rhythms are tied to natural cycles. Removing these cycles alters behavior and cohesion. Over generations, cultural degradation accelerates. The assumption that technology can replace ecology reflects a misunderstanding of scale and complexity. Technology is designed. Ecology is emergent. Designed systems struggle to replicate emergent properties reliably. This does not imply that off-world habitats are impossible. It implies they are inherently fragile. They require constant vigilance, intervention, and external support. They do not approach the stability of Earth. A multi-planetary civilization would require multiple independent biospheres capable of sustaining complex life indefinitely. No such biosphere exists outside Earth. Until it does, humanity remains ecologically bound to a single world. We can visit others, we can study them, we can build temporary refuges, but permanent independence remains beyond reach. Ecology is not an accessory to civilization. It is its foundation. Without a living planet, civilization cannot sustain itself. Earth provides that foundation freely, continuously, and resiliently. No other world does. As long as that remains true, becoming truly multiplanetary is not a question of ambition, but of ecological reality. Social systems collapse under permanent isolation. Human societies are adaptive, but only within specific environmental and structural boundaries. When those boundaries are exceeded, social systems do not gradually adjust. They fracture. Permanent off-world settlement forces human communities into conditions that amplify every known stressor, while removing nearly all stabilizing mechanisms that allow societies to recover from conflict, inequality, and failure. On Earth, societies rely on scale. Large populations dilute individual conflicts, allow specialization, and create redundancy in leadership, labor, and culture. Off-world populations are necessarily small. Small populations magnify interpersonal tensions because every relationship carries disproportionate weight. Conflict cannot diffuse outward. It loops inward. Isolation intensifies this effect. On Earth, people can leave hostile environments. They relocate, change professions, or integrate into new communities. Off-world, exit options do not exist. Every social conflict becomes permanent. Grievances accumulate rather than dissipate. Over time, resentment hardens into factionalism. Social stratification emerges rapidly in constrained environments. Access to critical skills, decision-making authority, or system controls confers power disproportionate to numbers. Engineers, medical staff, and system operators become indispensable. Their leverage reshapes governance structures regardless of formal rules. Equality becomes impractical when survival depends on specific individuals. Leadership succession becomes fragile. On Earth, institutions outlast leaders. Off-world, institutions are small, informal, and person-dependent. When leaders fail, retire, or die, continuity breaks. Authority disputes become existential because no neutral structures exist to absorb transition. Cultural stagnation compounds these pressures. Human cultures evolve through exposure, exchange, and novelty. Closed environments restrict input. Art, language, humor, and values loop internally. Over generations, creativity narrows, norms rigidify. Deviance is punished more harshly because cohesion is treated as survival. Psychological stress amplifies social instability. Confinement, monotony, and constant risk increase anxiety and irritability. Studies from submarines, polar stations, and space missions consistently show elevated conflict rates over time. These environments are temporary. Permanent settlement multiplies the effect. Family structures are also stressed. Limited privacy strains relationships. Reproductive choices become politicized when population size directly affects resource consumption. Children grow up under constant surveillance and expectation. Adolescence, already a period of social tension, becomes a systemic risk factor. Justice systems struggle to function in small, isolated communities. Impartiality becomes impossible when judges, juries, and defendants know one another personally. Punishment options are limited. Incarceration consumes resources. Exile is impossible. Leniency undermines authority. Severity fractures trust. Economic inequality reinforces social fracture. When resources are scarce, disparities become more visible and more resented. Wealth cannot be hidden. Privilege cannot be escaped. Redistribution becomes coercive. Voluntary cooperation erodes. Information control becomes tempting under these conditions. Leaders restrict dissent to maintain stability. Surveillance expands to prevent sabotage. Transparency decreases in the name of safety. Over time, governance drifts towards authoritarianism, not by ideology, but by necessity. Historical analogues support this trajectory. Isolated colonies, frontier outposts, and closed institutions show similar patterns. Initial cooperation gives way to hierarchy. Idealism gives way to control. The smaller and more isolated the group, the faster this transition occurs. Democratic systems suffer particularly. Democracy relies on pluralism, accountability, and the ability to replace leaders peacefully. In survival-critical environments, dissent is treated as threat. Elections become destabilizing events. Consensus is enforced rather than negotiated. Cultural identity also fractures across distance. Off-world communities develop norms suited to their environment. Earth-based values lose relevance. Mutual understanding declines. Over generations, shared identity erodes even without conflict. Education systems struggle to transmit knowledge accurately. Limited expertise concentrates teaching authority. Curricula ossify. Innovation declines. Critical thinking is discouraged when conformity is equated with safety. Religion and ideology often intensify in isolated societies. They provide meaning, cohesion, and justification for hierarchy. While stabilizing in the short term, they increase rigidity and resistance to change. Mental health support is constrained. Psychological distress cannot be outsourced. Therapists are limited. Privacy is scarce. Stigma increases. Untreated issues manifest as conflict, withdrawal, or breakdown. Crime takes new forms. Sabotage, hoarding, and coercion replace conventional theft or violence. The damage from minor acts becomes disproportionate because systems are tightly coupled. Social trust erodes as failures accumulate. Every malfunction invites suspicion. Blame becomes personalized. Cooperation declines precisely when it is most needed. Generational tension becomes acute. Founders accept hardship as choice. Descendants inherit it as fate. Expectations diverge. Loyalty weakens. Authority is questioned. Attempts to engineer social harmony through selection or training fail over time. Humans adapt socially through exposure and choice, not optimization. Removing freedom reduces resilience. Technology cannot resolve these dynamics. Communication tools do not create trust. Surveillance does not create legitimacy. Automation does not create meaning. Ultimately, social systems off-world trend toward fragility. They require constant enforcement, emotional suppression, and sacrifice. They do not self-heal, they degrade. This does not mean humans cannot live off Earth. It means permanent, independent societies face escalating social instability that technology cannot neutralize. Earth absorbs social failure through scale, mobility, and diversity. Off-world, failure accumulates. A civilization is more than survival. It requires adaptability, legitimacy, and shared meaning. Isolation erodes all three. As settlements persist, social cohesion becomes harder to maintain. Control increases, freedom narrows, creativity declines. The dream of harmonious off-world societies overlooks the social cost of confinement. Humans are social beings, shaped by openness, not enclosure. Without the ability to disperse, dissent destroys cohesion. Without diversity, stagnation sets in. Without renewal, collapse follows. Social systems, like biological and ecological ones, evolved for Earth. Remove that context, and their limits become visible. Permanent isolation is not a challenge humanity has ever solved. Scaling it beyond Earth does not change the outcome. The core limit is not technology, but civilizational dependence. The idea that humanity will become multiplanetary is often framed as an engineering milestone, but the deeper limitation is civilizational dependence. Human civilization does not function as a collection of independent modules that can be copied and deployed elsewhere. It is an interdependent system shaped by geography, scale, ecology, and shared infrastructure. When that system is divided, it does not reproduce itself intact, it fragments. Every off-world settlement concept assumes that a subset of civilization can be extracted, transported, and made self-sustaining. In practice, civilization emerges from dense interconnection. It depends on large populations to support specialization, redundancy, innovation, and institutional continuity. Remove that density, and the system loses critical properties that cannot be replaced by technology alone. Earth supports civilization because it allows mistakes. Systems fail without immediate collapse. Regions compensate for one another. Populations migrate. Institutions evolve through trial and error. This tolerance for failure is invisible but essential. Off Earth, tolerance disappears. Errors compound rapidly because systems are tightly coupled and unforgiving. Civilization also depends on layered time horizons. Some activities operate over minutes, others over decades or centuries. Infrastructure planning, cultural transmission, and knowledge preservation rely on long continuity. Off-world environments compress time horizons. Maintenance becomes urgent. Planning becomes reactive. Long-term thinking erodes under constant operational pressure. Knowledge systems degrade under isolation. Modern expertise is distributed across millions of people and institutions. No settlement can carry that depth locally. Over time, technical understanding narrows. Skills are lost. Documentation replaces mentorship. When unexpected problems arise, solutions are improvised rather than derived. Supply chains illustrate this dependence clearly. Earth civilization is sustained by global flows of materials, energy, and information. Even critical systems rely on components sourced from multiple continents. Off-world settlements sever these flows. Local production must replace global integration, but at far higher cost and lower reliability. Political systems face similar constraints. Governance on Earth is stabilized by scale and legitimacy derived from participation. Off-world, authority concentrates because survival requires coordination. Consent becomes secondary to compliance. Over time, governance drifts toward control rather than representation. Cultural systems also lose resilience. Earth cultures evolve through interaction and exchange. Isolation accelerates divergence and rigidity. Norms harden. Innovation slows. Cultural stagnation undermines adaptability, which is essential for long-term survival. The assumption that automation can compensate for these losses misunderstands what automation replaces. Machines can perform tasks, but they do not recreate institutional memory, ethical judgment, or social trust. Automated systems amplify fragility when human oversight weakens. Even if multiple settlements are established, they do not create redundancy in the way often imagined. Each settlement shares similar vulnerabilities. Energy dependence, ecological fragility, and social isolation repeat across locations. A failure mode present in one is likely present in all. Interplanetary distance prevents mutual support. Settlements cannot rescue one another in emergencies. Resources cannot be shifted quickly. Knowledge arrives too late. Redundancy requires proximity, not dispersion. The vision of humanity spreading across planets assumes that separation increases resilience. In reality, resilience comes from connectivity. Breaking civilization into isolated nodes reduces its ability to absorb shocks. This does not mean exploration is futile. Scientific outposts, temporary habitats, and specialized installations are achievable and valuable. They expand knowledge and capability. They do not constitute independent civilization. The distinction matters because rhetoric shapes investment and expectation. Treating off-world settlement as inevitable obscures the real constraints and encourages underestimation of risk. Civilization is not just survival plus tools. It is a continuous process of coordination across generations. That process depends on conditions Earth uniquely provides. As long as off-world systems require constant support, oversight, or replacement from Earth, they remain extensions rather than successors. Independence is not achieved gradually. It requires thresholds that current designs do not approach. The belief that future breakthroughs will erase these limits rests on faith rather than evidence. Physics sets boundaries. Biology enforces constraints. Social systems resist compression. Human history shows that even modest isolation reshapes societies profoundly. Distance magnifies those effects. Scale amplifies failure. This does not diminish humanity's achievements. It clarifies them. Earth is not a launch platform to be abandoned. It is the operating environment that makes civilization possible. Until another environment offers comparable support, humanity remains bound not by ambition, but by dependence. The question is not whether humans can reach other worlds. That is already happening. The question is whether civilization itself can be separated from the conditions that created it. So far, every line of evidence points to the same answer. Civilization is planetary, not portable.